Vamos a dar inicio al segundo día del workshop. Ayer fue un día bastante productivo, fue muy buena las presentaciones. Hoy día sin duda va a ser muy bueno también. Así que muchas gracias a todos por su participación, por su tiempo para poder realizar y ser parte, ¿no es cierto?, de este workshop latinoamericano en nanotecnología. Paola, ¿puedes dar inicio a las sesiones?
Hola, buenos días a todos. Les doy la bienvenida a esta segunda sesión, segundo día. A continuación, voy a presentar al primer conferencista de este día, el doctor Andrea Sile, de la Universidad de Minho, Portugal, quien presentará el trabajo titulado The Position of Cyber Nanocomposite on Textile for Control Antibacterial Activity Using Atmospheric Pressure Dielectric Barrier Discharge.
Obrigado. Graças. Eu vou fazer a apresentação em inglês, se não se importa. O meu portunhol não funciona muito bem. Só um momento.
Un momento, yo tengo que autorizar acá.
Quitarme os crens.
Ahí sí, ahí están autorizados.
Ok.
Había olvidado autorizar.
Muy bien. Gracias. Good morning. Thank you, firstly, for the invitation. My presentation is about my work, our work, the group here in Portugal, about the control the position of silver, but also other type of metal and metal oxide nanoparticles on textiles to control their effect during time. So we use a physical deposition method, use a plasma deposition. Our plasma deposition is developed for textile, so it's work in open air, in atmospheric pressure, without any gases, just air, in a continuous process. That is very important for textile application because of the cost that usually in textile have to maintain very low for competition reasons. So, as a brief introduction about this topic, I want to talk about the healthcare associated infections. This type of infection represent more or less between 4 and 6% of the deaths in the hospitals, and are increasing in the last years. So you see here, I have the data for the European hospitals, represent 6% of all the persons that enter in a hospital. 6% can be infected in the hospital by this type of bacteria usually. So this is an issue important to be addressed, not only in Europe, but all around the world. So which is the most important infection? Usually it's about respiratory tract, but also we have 4% about the skins, but we have also surgical sites, for example, that could be also in the skin or inside. Some infection the bloodstream, urinary tract, gastrointestinal, but we are not interested in this specifically for our work. Our work is more about wound care, is about skin or surgical scares. So it's about usually external or implanted textiles. So what is the main concerns about the healthcare associated infections? But firstly, obviously, the health risk associated with this, the cost for the hospital, for the society, and the insurgent of the antibacterial resistance. This because most of these infections are due to bacteria, a large number different and in quantity and in number of different antibacterial agent are used, and the widespread use of these medicines, no? The antibiotics have rise the bacterial strain with resist to this, and these are becoming more and more a worldwide problem that it's important to address or control. So we work with metal nanoparticle, metal or metal oxide, for be exactly. So why nanoparticle and why metals? So one is because metal nanoparticle have an effect that is very ubiquitous in the cells, means that attack different part of the bacteria and so can delay the insurgement of resistance, or single resistance at least, in some bacteria. Unfortunately, the bacteria are smart. So in the last year, some bacteria have developed also resistance to silver. So we have to use a technique that's very effective in a way to try to fight this type of resistance. So this is because we use nanomaterials. Nanomaterials could be very effective, very targeting exactly where we want to be affected at that time, and we can use a very low amount because they are very efficient due to the high relationship between the dimension and the volume available when they are in solution or deposited in a textile. So we can use at least between 100 to 1,000 less material than the use, for example, a salt of silver or salt of zinc. So also some type of metals, nanoparticles, have unique chemical and physical properties. Just we make an example. Copper, it's a very ductile material in bulk, in macro. But when we use nanoparticle of copper, for example, that also have antimicrobial effect, the copper became a super hard material. That's so the physical properties changes. This because of the dimension in the nano dimension. It happened, for example, also with the nanoparticle of gold. Gold in different nanosites have different colors, and this is used in nanomedicine, for example, to as an indicator of aggregation of the nanoparticle. For example, if is in the nanoparticle some kind of target material is used. So it's used the metal nanoparticle for antimicrobial, for antiviral, and also for anti-inflammatory reasons. Especially now in the last in the last year, because of the toxicity of silver, zinc oxide is widespread used for as anti-inflammatory, but also as antimicrobial nanomaterial. So, what do you say? One of the biggest problem of use silver, but it's very effective as antimicrobial, is the fact that one could be released in the environment as nanoparticle, and we want to avoid this. This is not good, and this is not only for the insurgent of resistance in the environment, but also because of the toxicity problem in the aquatic body, for example. And this is now an issue that is in discussion in Europe, that are preparing a legislation about this. Probably for in the next 2 years, we'll have a legislation that prohibits the use of silver nanoparticle in Europe. So, but one of the biggest problems of using silver, especially in the nano phase, is their toxicity, cytotoxicity, and also genotoxicity to human. So we are very careful to use silver as antimicrobial. And one of our main concern in our work is to avoid the direct contact of the nanoparticle with the body, and also to immobilize the nanoparticle very tight to the substrate in a way that don't go outside the nanoparticle or can be entered in the bloodstream or direct in contact with the skin or whatever. So silver have a very different effect that are effective in the bacterial cells, but in large amount or large concentration could have also effect in the human cells. So we want to avoid that. So what we have done to do that? So before we prepare the nanoparticle dispersion in a sol gel, usually, we prepare treat our textile with plasma. When we deposit the nanoparticle in the textile, to be sure that's very tight connected with the textile, and then we use different type of polymers or coatings to control the contact of the nanoparticle or the dissolution of the nanoparticle during time, to be sure that only the ions of silver or zinc, only the ions goes to the target bacteria, and not the nanoparticle. So we use them to treat our materials. I will say this is our plasma machine. It's working in air, but it's prepared also, you see here the tubes. It's also prepared to work with other type of gases, but for our work usually prefer just working in air. It's a continuous machine, it's a roll. We can treat a large amount of textiles. And we use a double dielectric plasma, means that the roll here and the electrode here are dielectrics. So this is ceramics, and this is silicon. The plasma, you can see the plasma form here, and we can control the velocity and the power of the plasma and treat the textile. What happened to the textile is that the textile becoming, usually we use polyamide of polyester, and a lot of oxygen is included in the surface, only in the surface. This is good working with plasma because it's effective only on the surface of the material, don't change anything else, and can add a lot of functionality to the material, like especially oxygen in our case, producing hydroxyl or some ozone-like molecules, very high reactive oxygen species. That's when it enter in contact with the nanoparticle, linked together very tight. So the nanoparticle going to go So then we have tried different type of deposition of the nanoparticle. We have tried with ultrasounds, the position, that is very effective because the nanoparticle is practically through very high velocity on the fiber. But how you can see, it's very difficult to treat big, large amount of textile. So we have discharged this type of application, which is very expensive to treat and treat very small type of material at a time. So we have tried a deep coating, just dipping the fabric on the nanoparticle solution. We have tried the spray, and also we have simulated a dyeing step, like a dyeing of a textile. So it's with basculant agitation at a specific temperature for a specific time. This we will see that is the best method because it reduces the aggregation of the nanoparticle and have a sprayed deposition. So also we have tried to control with the HMDSO, that is a silicon material that produces a film that can protect the deposition. So we have different layer. We have the first layer, just the deposition of the nanoparticle with or without HMDSO. A second layer just of HMDSO with different method, and eventually a third layer in the case in which the nanoparticle are in the middle. This is named, so we have sprayed just HDMO, then the nanoparticle which HDMSO, and then HDMSO again. That means it is a sandwich-like deposition. So we have tested also the contact angle. So means it's higher is the contact angle, more hydrophobic is the surface. Means that, for example, hydrophobic in case of reduced bacterial adhesion, but more hydrophobic is the surface, more reduces the bacterial adhesion, it's better because it's not easy to produce a biofilm, the bacteria to produce the biofilm attached to the surface. So you can see that in the case of DBD, obviously we improve the hydrophilicity, not hydrophobicity. This is because the high amount of oxygen that's we introduce with the DBD. So in a case, it's good because we improve the adhesion on nanoparticle and the materials, but at the same times, we also improve the absorption of bacteria. So it's like half term of this. So we can see here it's the untreated material and the plasma treated material. In this case, it's polyamide fibers. How you can see the black dots here are all the nanoparticle of silver. Okay, it's more or less 20 nanometers. How you can see our method, it's not only able to introduce more silver, but also to improve the dispersion it's more dispersed, more even all around the surface of the fibers. So we also use the diffuse reflectance because we use the property of silver to absorb in the visible light. So more, this is the reflectance, okay? More reflectance, indicates that you have less silver. So we have to reduce the reflectance, more absorption means that we have more silver in the surface. So what happened here? It seems that after DBD, we have less silver, or very few amount of silver in the surface. But after washing the surface and remove the first layer of HDMAO, we can see that the silver is there. So after the washing, appear the silver. So, and obviously we have done the gram-positive and gram-negative antimicrobial effect of our results. So you can see here is the effect of log reduction. So higher is the reduction, better is the antimicrobial effect. You can see that the best results are obtained from gram-negative bacteria, E. coli, and the worst with gram-positive. This is probably because the nanoparticles are tightly immobilized on the substrate. The only effect is due to the silver ions that are released slowly to the substrate to the target. That means that probably the ions have some problem to go through the thick peptidoglycan membrane of the gram-negative, but are able to destabilize easily the cell walls of the gram-negative. So anyway, we can see here that we have some results respect to without the use of plasma, but are just a bacteriostatic effect, not bactericidal. Bactericidal effect very well is more than 3 or 3 log reduction, it's bactericidal. So we have obtained some good results, but at least for now, just for gram-negative. The big problem now is that after washing, a lot of things changes, and for now we have no good results after washing. This is probably not because the nanoparticles are not linked, but because it's there, the silver remains there, we have to check it. But because of the oxidation of the silver, probably that's slowed down the effect. So we are also working on to improve this part. So what happened is we have use a higher amount of nanoparticle and silver to have because we think that also the problem was a very low concentration of silver that we used. So now we have a step to analysis 1 milligram per milliliters of silver nanoparticles after 2 hours and after 24 hours. This is because we want to see the effect through the time. Remember, we have this coating that should be protected the nanoparticle from the bacteria and allowing only the ions to be released. As you can see, we have used also chitosan as a polymer to control the release. So what we can see here is the log reduction of during time at 2 hours. We have no difference in effect with the use or without the use of plasma deposition. But after 24 hours, the difference are huge. As you can see, without plasma that's immobilized the nanoparticle, after 24 hours, all the silver is depleted because it's go through and go out from the fabric. But the silver that's immobilized by plasma it's there and continue to be a very good effect in log reduction. So it's working, and we can control the release of the silver during time to maintain there. This is also that the initial results of 2 hours for the gram-positive became more expressive after 24 hours. Means that the silver is there, how you say. And also you can see without plasma, the black ones, it's reduced during time. But with plasma, we continue to have a very good log reduction. Means that now it's working also with aureus, which means gram-positive, and this was due to the concentration. That's in the initial part, we have working with too low concentration, and now we have fixed this part. So this is our last results, that are encouraging, but we want to go further to control for more than 24 hours. So it's a working process, but we want to arrive to control the release of nanoparticle of the ions of silver for at least a month to be prepared, for example, as we will see in the presentation of George Padrão, after me, is the immobilization of this nanoparticle in net for implants for hernia mesh. So I want to thank you, all of you, and my collaborator for the work and for the invitation of the Universidad de la Frontera, and thank you very much.
Muchas gracias por su presentación. Muy interesante tema. A continuación vamos a dar paso para algunas preguntas. Tenemos algunos minutos.
Pueden hacer por el canal de YouTube las preguntas o por este mismo medio. Bueno, yo tengo una pregunta. I have a question. So what kind of nanoparticles do you use? Chemical or biological?
So now we are, all the work here presented, it was with silver nanoparticle. This nanoparticle was prepared by citrate reduction in solution in a two-step. To control the dimension, we use a two-step. The first step is preparing 4 nanometers nanoparticle, or dots. And then we reduce to control the starting from these seeds to control this the growing of the nanoparticle up to 30 maximum nanometers. So we use usually 20-30 nanometers nanoparticles of seed. But we are working now. We start working now with the gold zinc oxide nanoparticle also, because are less cytotoxic.
Okay, thank you. I'm sorry, but I didn't understand well how the nanoparticles are linked to the textile. I mean, by the plasma, but is there some electrostatic interaction or?
Yes, it's a very strong electrostatic interaction. Okay. It's a quasi-covalent connection. It's not covalent. We prove that because we can see in the FTIR, but it's very, very strong because it resists to the washing process. And we will see that after washing, we have to do the SEM, the scanning microscope. We will see that remain there. It's the plasma, it's just treated, the textile. Then we do the immerse the textile on the solution.
Okay.
So it's linked.
Thank you. Thank you very much.
Thank you.
So are there other questions? I think.
Andrea?
Any question?
Yes.
A question. you could use this system for other nanoparticle types, for example, copper or other antimicrobial nanoparticles for deposition in textile,
Yes.
or only exclusive for silver?
No, we are working with zinc oxide now. We will start working with gold now also. We have done some experiment with titanium oxide, but it's for another application, because titanium oxide is very cytotoxic for the skin. It's very irritating because produce in contact with the UV produce peroxide. So it's not good for the skin. But it's very good to degrade molecules. So we can use in, for example, bioreactor for degradation of antibiotics. And we have immobilized also other type of nanoparticles.
Mm-hmm. The retention time for all nanoparticles is the same, or is different in the textile?
What intent for the retention time? The time that they remain to the in the textile.
Yes.
Okay. It's dependent not only by the metal or the metal oxide that's used, but also of the type of link and the type of polymer that's used. Because this nanoparticle is protected by a polymer, it will be degraded slowly, obviously, but also depends to the environment that we use. We immerse in water or live in air, the degradation is different. So we have to control and measure the kinetics every time we do this work. It's different.
Okay, thank you. Very interesting, your work.
Preguntas, more questions?
Creo que no hay más preguntas.
Ya. Muchas gracias por su presentación, por dar una charla de un interesante tema. Vamos a continuar entonces con esta jornada con el doctor Alejandro Pérez de Luque, de IFAPA España, quien nos va a presentar el tema de Hypatia Project, From the Synchrotron to the Field.
Buenos días, buen día. Can you hear me?
Yes,
¿Se me escucha bien?
Yes.
Se escucha bien.
Voy a compartir la pantalla. Creo que tengo un problema para compartir la pantalla con el navegador. Vamos a ver. Creo que voy a tener que reiniciar desde otro navegador porque no me deja desde compartir la pantalla.
Si quieres, Alejandro, envías la presentación al email del workshop y yo me vas diciendo siguiente, yo la voy pasando por acá.
Vale, vamos a ver. Voy a ver si puedo reiniciar desde el...
Ajá, ok, esperamos.
Un segundito desde... Vamos a ver. Vamos a ver, voy a salir un momentito, ¿vale? Y entro.
Bueno, mientras llega Alejandro, soluciona su problema, recordar que a todos los speakers y a las personas que presentaron póster, enviar antes del 7 de diciembre un abstract. Por el email fue enviado un abstract template para poder elaborar el libro de resúmenes y poder enviárselo a todos.
E também queria lembrar a todos da sessão de pôster, que podem acessar, todavia está disponível para todos.
Ya estoy, a ver si me deja disculpar. Vamos a ver.
Ahí sí.
Se ve ahora mismo, ¿no?
Sí.
Vale.
Ajá.
Vale, bien. Bueno, pues voy a darle a iniciar. Correcto, se ve, ¿no?
Sí.
Okay, I will do the talk in English because I know that there are international. This is an international meeting, so there is people from other countries, and my portañol is not good, also. So I prefer in English. So I don't mind to answer a question in Spanish, and I can understand Portuguese. So no problem after the talk for that. All right. So. Well, my talk is about a recent project that we have finished during this year, and it has been lasting for the last 2 years in collaboration with several institutions. The acronym is IPATIA, and the name is, as you can see here, is Romancing the Stone, Size Control Hydroxyapatite for Sustainable Agriculture. IPATIA is shorter, so it's easier to talk, to pronounce. Well, in this project, we have been involved with 4 institutions, 2 from Spain and 2 from Italy. The Institute of Crystallography from Italy, the University of Insubria, and also the University of Granada from Spain, and IFAPA, that is the Institute for Research and Training in Agriculture and Fishery, that is the institution in which I belong. There is, well, I share the authorship of this work with all these people. There is also more involved, but mostly for this, the work that I'm going presenting here, these are the people that have been involved. And if someone wants to contact me for further interest in the work or any other kind of question or anything else, I will be happy to attend you in this email. So I have divided the talk in different parts. And so let's go for everyone, and let's start with a short introduction. I want just to know that some of the things that I will tell here, because despite they are oriented to the nanofertilizers, many of them can be applied also for any kind of agrochemical. So just keep in mind that they can be generalized for other agrochemical, for pest control and all these things. The first question is why the title for the talk? Well, because I can't stop to wonder and amazed about how can we use very advanced techniques and very advanced, very complex machinery in order to develop tools for an activity like agriculture that we started more than 10,000 years ago. And in this case, well, not me, but the people in charge of the characterization of the nanomaterial, they have been working with a synchrotron, a particle accelerator, in which they use the facilities available in order to characterize the nanomaterial. And it still amazes me that we have used that in order to go to the field later for just trying to feed the crops. Because that's the reason we did this research, is because we want in some way just to improve the way that we use for feeding the plants. As you know, I'm trying to explain here with some pictures a comparison between the conventional fertilization that we are using at this moment with nanofertilizer, or what we want to do with nanofertilizer. Usually for plants we need 3 of the most important nutrients that we call macronutrients, that are nitrogen, phosphorus, and potassium. Nitrogen usually by far is the most important for agricultural production. And this is what we get usually when we go for conventional fertilization: a lot of food for the plant, a lot of nutrient for the plant. With nanofertilizers, we want to go for a smaller, amount of nutrient for the plant. Why? Because this is the problem that we have with the conventional fertilization. We waste a lot of resource. There is a lot of nutrient that the plant is not able to assimilate and use. A big amount of these nutrients are wasted and are lost with all the environmental and economical problems that it causes. And with nanofertilizer, that should be the idea, just to get the right amount, or almost the exact amount of nutrient that the plant needs. But we don't want just to get this effect also on plants fed with nanofertilizer. We want that they produce and they grow in the same way that with conventional fertilization. So keeping that in mind, here you can see a brief picture of research today regarding nutrients or nanofertilization and crops. This has been taken from this review, our recent review by Kopitke and collaborators. And you can see how there are the works that we have found regarding, for example, nitrogen fertilization, and the crops in which it has been studied, in this case only with rice, is something that was strange for us, because nitrogen, the main nutrient for crop production, is the less study regarding nanofertilization. And there are many others, just with, for example, for phosphorus and many different other crops, magnesium, all other micronutrients that are not as important as the NPK nutrient, but also important for many crops, because can produce problems when they are in a deficient manner. One thing that I would like to point out is that compared with nanomedicine, or with application in pharmacology, nanomaterials and nanotechnology can lead to problems regarding the consumer risk perception in agriculture and food production. Why? Because if you think about that, we are not going to assume the same risk if we need a treatment for a disease, for example, for cancer or a serious disease that we can have, compared with the risk that we can afford if we are going to eat an apple, for example, or any other food. And this is clear because for a disease treatment, if we have a serious disease, we don't mind to get some collateral or side effects if they are not very very dangerous. Sometimes even being dangerous, but we don't mind to have some side effect. But we are not going to get we cannot afford those effects with food production. So this is something that very important that we need to keep in mind. This links directly with the problem of toxicity of nanomaterials, that we can find that they are toxic for for the cells, what we call the cytotoxicity, or they can be toxic for the plant. They can accumulate in some areas and be toxic for the tissues in that areas, or the plant can tolerate that. But then if we feed the animals with those plants, they can accumulate in the animals and they can cause problems in the animal. Even in the case that we don't have problem with any of them, and the animals and plants can safely just introduce those nanoparticles as part of their organisms, finally they can go on our tables. And then we consume then those products that can have nanoparticles or nanomaterials, and we need to be sure that they are not going to accumulate and produce further damage in our organisms. So we don't want to finish with nanotechnology being like a banned technology in agriculture, like or something that has a bad reputation, like happened with GMO. And this is a task that we researchers need to consider and have in mind. Another difference that we need to keep in our head is that in medicine, usually we have individual treatments. We go for an individual and we apply the treatment just with injections or whatever. In plants, in agriculture, we need to go for mass treatment in the field, in the environment. And it means that we don't have control on where all these nano devices and all these chemicals will finish. Probably some of them will spread around the environment, and it can bring new problems. Also, something that we need to consider is how we can scale up the production of this nanomaterial, because this is an issue that they have found in many of them. And just when we start to test in a few plants, usually it's not a problem. When we want to go into the for field application, just working in the field, we need a huge amount of nanomaterials, and it's not easy to produce just from the laboratories or the companies with which we collaborate. That is another problem. In addition, we need to consider that the production expenses, farmers usually spend around 10-12% of the production cost in agrochemicals, either for plant protection or for fertilizers or soil improvement. So it means that the fabrication cost of the nanomaterials should be lowered and cheap enough for the farmers to afford that cost. So it means that probably using gold nanoparticles is not a good idea in this case, despite it could be for some, perhaps for some crops with high inputs and high costs could be affordable, but not for the common one. So the ideal nano device should be non-toxic and environmentally safe. It should have an easy way for scaling up the production and made with low-cost material. In this case, we found that the nanohydroxyapatite probably could fit within all these things, and we started to work with that. Then, how we apply fertilizers? Usually, we have two methods for that. One is applied in the aerial part, in the leaves. We apply them just spreading like a spray. The problem with that is that external agents, for example, the ultraviolet light or many other agents, the humidity, cold, temperature, etc., they can destroy the agrochemical that we are applying. In the case of this, also we need to consider that sometimes we need these need to go inside the plant. They cannot stay on the surface usually, or sometimes probably we need that they stay. If they are agrochemical for just fighting pests, probably they need to stay on the surface and remain there and not going inside because the pest is going to extend on the surface of the leaves. So we need to consider that. Also, we can apply them with irrigation. It means that in that case, the nanomaterials, the fertilizers, the agrochemicals will interact with the organisms that we have inside in the soil, either microorganisms or macroorganisms, and also with all these components of the soil, like the organic matter, salt, ions, and everything that can alter the behavior and the properties of the active matters, active components, the chemicals, and the nanomaterials themselves. And then, if we solve all this problem, all this interaction, we have the plant uptake problem. If we apply through the leaves, they need the materials and the agrochemical, they need to cross many different tissues until they reach the vascular tissues, the vascular area where they can spread all around the plant, or they reach the right place to have effect. And also with the roots, despite this is an organ that is specialized in absorbing nutrients and water, and could be easier for nanomaterial, also they need to cross different barriers until they reach the vascular cylinder and the vascular area, including the endodermis, that is usually a very strong barrier for the solid chemicals and all these things. And then we need to consider also how these material move inside the plant. We have basically two kind of pathways in the plant. One is the apoplastic pathway, that is when they move outside the cells, but very often they need to go into the symplastic pathway. It means that the materials, chemicals, water, etc., they need to go inside the cells, because the plant in that way can select what kind of material go in or out the plant, until they reach either the phloem or the xylem for just move along the plant. So what is the goal that we have in this project? Well, basically what we wanted to do is just reducing the amount of nitrogen that we can apply during in a normal crop cycle, but at the same time we need to keep and maintain the levels of yield and the quality of the product that we are obtaining. If we can get this, that should lead to first, on one side, a lower environmental impact, because we will waste less nitrogen, and on the other hand, we can increase the profits for farmers, because if the farmers have a lower input cost and they maintain the earnings, it means that they are earning money, so they are saving some money, so they are increasing the profit. So we went for some brief words about the experimental designs. All this data and information that I'm giving here, you can find in two recent published papers about all this work, that they are open access, so you can go for them and just check for them more in detail if you are interested. And because I'm not specialized in the synthesis and characterization, I'm more on the agronomical part, I will briefly describe the synthesis. We basically went for a precipitation method in which all the people in charge in the University of Granada, mostly, and part of the people from Italy, they were just using this method for just creating the urea with the nitrogen source nanocomposite. And then they the characterization with just using different techniques, including scanning electron microscopy and small angle X-ray scattering. Here you have a picture of the material that we get for the experiment, and they provide us with this nanocomposite. And then we just tested them with durum wheat, Triticum durum. That is it's a very important wheat that we use in Spain and Italy for just pasta, for producing pasta. So it is quite important in the south of Spain. And we did three different treatments. One untreated, and the control conditions, we were not able to go into the field because some different problem and also the lack of time for all this. But we did the experiment under controlled condition with untreated plant. That's it, with no fertilization, only with the nutrient that they have in the soil. Then we use conventional fertilizers for comparison with the treatment that we were giving with the nanoparticles, with the doped nanoparticles. And what we did is, for the conventional application, we went to traditional application compared with the one that we use in the fields in Andalusia, and that is with some amount of nitrogen, soil placement before planting the plant, and then usually in Andalusia we go for 2 top dressings with 90 and 60 nitrogen units. But in the case of the nanoparticles, this amount was lower, was about 15 units, because we reduce the amount of fertilizer with the nanoparticles in order to compare with the conventional treatment. We gave this treatment in a different stage development of the crop. The first one at the beginning, when before just the seeds were sown, and after that we apply when during the stem elongation in this stage, just before the grains and the kernel start to develop. And this are briefly the result that we got with this experiment. Firstly, we went for just measuring the yield components in order to know what we could get with this reduction in fertilization. And we found that with the conventional fertilizer, we got a higher shot number compared with the nanoparticle treatment. That means because usually in wheat, from one seed, we get more than one shot, because it's something very important, is because it makes for us sure that we will get more yield. So in the case of the conventional fertilizer, we got more than with the nanoparticle, and in both was higher than with the untreated control, as we were expecting. It was around 3.5 and 4 with this. However, the plant weight was the same for both, and as you will see now, it has an explanation, because regarding the ear number, we found no difference between the conventional and the nanofertilizer treatment compared with the untreated. And the ear weight was also the same. This means that, going back a little bit, it means that in this case, we have probably an excess of fertilizer, and the plant is producing shoots that are not going to produce ears later. So it means that we are just wasting part of the nutrients in a vegetative growth for the plant that is not going to production for yield. Regarding the kernel number, we found different here. The nanofertilizer treatment just lead to a higher kernel number or grain numbers compared with the conventional one. And of course, both were higher than the untreated control. And the kernel weight, in this case, was the opposite. The conventional fertilizer just produced less number of grains, but with a little bit higher weight. And this one, with the nano fertilizer, we got a higher kernel number with a smaller, a little bit smaller than the positive control, that conventional treatment. However, in the end, we got the same yield for both treatments. So that's a very good news for us, because it means that we can, at least under control condition, we can get the same yields, just reducing the amount of nitrogen. So as a summary in this case, we with the UACP with a nanofertilizer treatment compared with the conventional, we got slightly less shot number. So it means that we are just not wasting nutrients just in aerial parts growing with no yield results later. We got a higher kernel number with a slightly smaller grain. So there is a compensation in this case that leads for a similar yield. Regarding the kernel quality, it is important. For that reason, we also selected durum wheat, because for pasta fabrication, we need what we call the hard vitreous kernels. Here you can see these two pictures. This is a vitreous kernel, hard vitreous kernel. They have the kernel, when you cut the grain, they have a hard, like a glassy, like a glass aspects. When they don't have this structure, they are more like flour, than the one they use for bread and all these things. And we need this one. And this depends also on the protein content in the kernel. It's very important, the amount of protein that we have in the kernel. And the nitrogen is very important for that. So when we compare, we found that the percentage of beetroot kernel was the same, was not different in both treatments. And only the protein content with the nanofertilizer was a little bit lower compared with the conventional fertilizer. However, in both cases, this less protein content was still above the 13%. That is the minimum the threshold that we need for just the highest quality group when we commercialize these varieties. So it means that we can get still the highest quality with reducing the amount of nitrogen. So both things, the same yield and the same quality, are very good news for this for the results for this project. In addition, we performed some quick experiments in order to elucidate how the nanoparticles could go inside the plant. And we check in the roots and the leaves, just using the staining of this nanoparticle. We're using alizarin red S, because this is it stains this kind of nanoparticles, and also cells that are rich in calcium. And then we were able to detect that in the roots, the most important thing is that the roots can uptake this nanoparticle very, very quickly. After 1 hour after application, we were able to detect these nanoparticles inside the roots. Here you can see in the cortex, and just moving apoplastic from the apoplastic. And when they move, they cross the endodermis and they go inside the central cylinder. We were able to see that they were just moving in a symplastic way until they reach the xylem, and they just move through the plant. However, for the leaves, it takes longer, about 48 hours after the application. And we found that they were able to go inside the plant through the stomata, at least at the level that we were able to study. In this case, these two belong to the same sample. Here we can see the outer part of the plant. Here we can see an stoma. Okay, it's an stoma that is at this moment is closed because of all the treatment and all this. And we were able to detect under the stoma some different some coloration that when we go on focus, we were able to detect that they were the nanoparticles staining with the alizarin red technique. So it means that they go inside and they go through the stomata and reach the stomatal cavity, and from that they can move to through the apoplastic way to reach the vascular tissues. So as a summary, what we got in this project in this last part, the application of this nanofertilizer leads to allow for a reduction of about 40% of the total nitrogen, and around 24% of the phosphorus that we were applying. The efficiency of the nitrogen and the phosphorus usage was around 6:1 and 1:1 respectively for a 500 kilograms for hectare application. We got the same yield at the end of the crop cycle and the same kernel quality, so it's quite important for us to maintain all this all this level, just reducing the amount of nitrogen applied. And we observed that, at least with this preliminary result, the uptake is better through the root than through the leaf. It means that we should go for application in the soil, but it's possible we want to study further study about this, that the leaves can also be used for just some application in some cases. Further work that we would like to do in this case for the just after this project, always if we get financial support for that, well, future field test. The field test for agronomy are like the clinical tests and the clinical trials for medicine. If we don't go to the field, just forget it. It can work very, very well under controlled condition, but the the real test in order to know if a technology is going to work is the field. So we are working, well, our colleagues at the University of Granada in Italy, they are working in just escalating the synthesis, and also working for increasing the nitrogen content in the nanoparticle. So if we are lucky and we get financial support for that, we expect that in following years we can go for trial works with it. And well, finally, just I would like to thank my team in Cordoba, my colleague, the Dr. Josefina Sillero and Cristina de Miguel, who they were just helping with all these agronomical trials and works. And thank you for your attention. If you have any question, I will be happy to answer then. And also, if you want to contact me later for some other reasons, no problem for me. So that's all.
Muchas gracias, doctor Alejandro, por su presentación. Muy buen tema, todo un desafío para el futuro. A continuación, damos un par de minutos para algunas preguntas. We have time for questions.
Ok, aquí tenemos una pregunta de María Mercedes Martínez, que pregunta si tiene información sobre interacciones posibles de componentes de la nanopartícula en la disponibilidad de otros nutrientes o en la SIC del suelo, por ejemplo.
Pues vamos a ver, hay en concreto sobre la disponibilidad de otros nutrientes de estas nanopartículas, ahora mismo no tengo datos. Creo que había un trabajo hace poco que se ha publicado en Scientific Report en una Special Issue, que estamos en una colección especial precisamente sobre nanotecnología en agricultura, y habían trabajado sobre la interacción de estas nanopartículas con microorganismos beneficiosos del suelo, que en principio veían que no había interacciones negativas, porque además al tratarse la hidroxiapatita, al tratarse de un componente natural, eso no lo he comentado, es un componente natural de los huesos, tanto de animales como de personas, incluso de las raspas del pescado y otros animales, pues no suele ser un problema de interacción con otras cosas. Eso sí, es posible que haya en un momento determinado, pero no por la nanopartícula en sí. Puede haber interacciones por los nutrientes que estemos aplicando. Y sí es cierto que en temas de fertilización hay interacciones cuando aplicamos unos nutrientes con respecto a otros.
Ok, muchas gracias.
May I have a question?
Adelante.
Okay.
Okay, thank you, Alejandro, for the presentation, a very didactic presentation. It's very nice to see these results. I remember some years ago in Sorocaba that you were just beginning the project.
Yes.
Now the results, it's very nice to see them. Very positive results. Also some information about the mechanism, about the uptake of the translocation of the nanoparticles. So congratulations. Just one question. Why did you choose this proportion between nitrogen and phosphorus? Because the proportion of nitrogen is low compared to that of the phosphorus.
Yeah, because
the demand in the soil, you have more, you need more phosphorus. I don't know. And also another question: why did you choose urea as the nitrogen source? Have you tried with ammonium or nitrate, for example? Because in the conventional fertilizer, you usually use the ammonium.
Yes, it's because the problem was because at the beginning, the groups just in charge of the synthesis of the nanoparticles, they were trying with different form of nitrogen. They tried with nitrate, with ammonium, with urea. And the problem that it was that during the synthesis, they interfere with the process. So they cannot get proper nanoparticles of either hydroxyapatite. So we went there. We saw that the urea is the best one for just going incorporate inside the structure. Indeed, they have not only urea; they have some ammonium. I think ammonium or nitrate. I need to check. I'm not sure which one of the two. They were able to incorporate part of as ammonium or nitrate, one of the two, inside the real structure. So it's a nitrogen that is going to be delivered very slowly when the nanoparticle just degrade, and also in the upper side of the inside, but absorb inside the nanoparticle properly, they were able to introduce the urea, and it's going to be released a little bit faster. So the problem was basically because of a problem of the synthesis. So we went for that. We wanted to try with different ones, but that was the best solution. Sorry, what was the other one you asked about the?
I think you answered.
The phosphorus and yeah, because usually phosphorus is not a problem in our soils. We went for that because we know that in some other cases phosphorus is important, and also the nanoparticles are very rich in phosphorus. So we use that also, but as a secondary thing, because basically phosphorus is not a problem in the soil that we are usually managing. We usually don't apply phosphorus there. But we know that can be very interesting for other crops. For example, I know that there are a lot of studies with these nanoparticles for legumes.
For soybean, I was thinking of that because in Brazil, for example, you have a very acidic soil. Phosphorus is a problem here. So this one would be great for soybean production in Brazil.
Yeah, so you don't need so much. I know, but for us, it's not a problem. So we just forget a little bit because we need to focus on one of the two problems.
But
so we went for. But I know that for soybean is a good point. However, there is a discussion also because in that special issue about nanotechnology and scientific report, there is another paper just dealing the same paper that is dealing with that there is no problem. An interaction between the these hydroxyapatite nanoparticles and the microorganisms in the soil. They say that they found no good release of phosphorus for the plants. However, we have also some data, and I think that it is also published that it seems that that the form of the nanoparticles and the structure of the nanoparticle can influence all this delivery of the phosphorus. So there is place for debate and for studies and for all these things. So it's so if you're interested in phosphorus applications, we can just talk about that. So
yeah, sure.
I'm happy.
Okay, thank you, Alejandro.
Thank you.
Gracias por la respuesta. Aquí tenemos otra pregunta de Leonardo Fernández Fraceto, del doctor Fraceto, que dice: Congratulations, Alejandro, primero que todo. Y después nos dice, it is very interesting that you can decrease the amount of fertilizer with your system. Do you believe that the nanosystem in the field can take long effect? I mean, after the end of some crop, the amount of nanofertilizer that was as a residual in the field could be able to be used in the next crop?
No, I don't think so, because at least in the condition that we have in Spain and in Andalusia, because usually, well, these nanoparticles, when you apply, we did some tests and in some experiments with in the laboratory, with just washing them through the soil, so soil columns, and they can be washed in a very lower amount compared with the conventional fertilizer, but they can be washed with time. So if we are applying a very reduced amount, the idea is that it's not going to be when the crop finishes, the nitrogen should have been incorporated into the crop. So the idea is that there's not remnants or residual nitrogen there. If we want to keep nitrogen in the soil for the next crop, the best option is just legumes. Going for a leguminous crop, just collect the crop and just leave the residue there, because this is a good nitrogen for the next crop, and this is what we are doing now with the rotations in Europe and in Spain. We are going back to all practice, just rotating just cereals and oleaginous crops with legumes again. So I don't know if I have answered the question.
I think so. It's clear. Thanks a lot. And we have the one last question is from Andrés Sampaio Ferreira, and when he says, "Congratulations, Dr. Alejandro." And the question is, do you believe that nanotechnology can change the mobility of nutrients in the soil?
Well, it's a very wide question. I'm not sure. The idea or the goal is that it should change the less possible that kind of exchange of nutrient, because the idea is that we can deliver the exact amount or the most exactly amount of nutrient that the plant needs or the crop needs when it demands it, and not interfere in the less possible with a normal cycle of the soil. Of course, we are just interfering with the soil. We are just farming. But if we want to have the less disturbance in the soil after that, and avoiding just leaching and just getting problem in other places because the excess of nutrients are being washed and leaching and going into subterranean waters and all these things, I think that nanotechnology, probably not only nanotechnology, but nanotechnology is a tool that could help with that. El micrófono no puedo.
I'm so sorry, my microphone was quiet. Thank you very much for your answers.
Okay, thank you for the invitation.
Gracias por su presentación, doctor Alejandro. A continuación, seguiremos entonces.
Sí,
seguimos con la siguiente charla.
Olá, bom dia a todos. Eu espero que me estejam a ouvir bem e a ver.
A continuación vamos a seguir con nuestra tercera conferencista de esta mañana, Helena Figueiras, de la Universidad do Minho, Portugal, quien nos presentará el tema biodegradable with span engineered delivery vehicles of natural occurring active biomolecules for the eradication of gram-positive and gram-negative bacterial-derived infection. Thank you.
Ok, olá, bom dia. Eu também vou fazer então a apresentação em inglês para que toda a gente consiga perceber. Antes de mais, só queria agradecer à organização pelo convite. Tenho todo o gosto em falar sobre este tópico. My name is Helena Felgueiras. I'm a researcher at the Center for Textile Science and Technology from University of Minho in Portugal. And today I'm going to show a little bit of the work we are developing in our team. So it's about the wet spinning of biodegradable polymers and using them to load biomolecules to act against bacteria involved in infections. So what we did here was to produce wet spun microfibers using the wet spinning technique. In here we combined biodegradable polymers, in this case the polycarbolactone and the cellulose state. We blended them, and then using a coagulation bath we created microfibers. After having these microfibers, we immobilized on the surface of these microfibers 3 essential oils, our active biomolecules, using physical binding to bind them. This particular case were the cinnamon leaf oil, the clove oil, and the cashpoit essential oil. And then we examine in each way they would be effective against 2 types of bacteria. In this particular case, we used the Staphylococcus aureus as a gram-positive bacteria and the Escherichia coli as a gram-negative bacteria. They was just selected as examples of the action these oils could have when binded to the surface of the fibers. Okay, so Dr. Zil already told a little bit in his presentation about bacterial infections and the role they play nowadays in our health system. So what we did here was to look at the most prevalent bacteria, which are a very large number of them that cause infections in the human body. In fact, if you look at the recent projections, we actually know that approximately 10 million annual deaths are predicted to occur in 2050 due to bacterial infections. So this is a very serious concern that is affecting our community nowadays. In this particular case, we're looking at the Staphylococcus aureus and Escherichia coli, but like I said in the beginning, these are just examples of the bacteria types that we used as an example to test the efficiency of our strategy. So for those of you that were not yet logged in on this presentation or this workshop today, didn't hear from Dr. Zil, for those of you that don't know, the antibiotic synthetic agents are one of the most conventional treatments opportunities or options for nowadays to treat bacterial infections. They are capable of targeting the cell wall of bacteria and induce bactericidal effects. Unfortunately, due to their overuse or ineffective use or even misuse, the antibiotic resistance of pathogens, or especially bacteria, are rising. So they are turning ineffective. And for that reason, we are looking at different strategies, alternative strategies to treat infections caused by bacteria. In this particular case, the recent research has been focusing on natural extracts, namely essential oils. Essential oils can be produced by a wide number of plants, and they have been used in Chinese medicine or alternative medicines for a very long period of time. And nowadays they are entering Western medicine as well. So these biomolecules, the interest of these biomolecules is basically on their antimicrobial performance and their regenerative potential, namely its antioxidative effects and anti-inflammatory effects. That's why we are selecting them as an alternative. However, they present also some limitations to their use as conventional medications for treating infections. And one of those is the fact that they cannot be used in high concentrations because they can present cytotoxicity to the human cells. So they cannot be delivered in a systemic way. Also, they can present low resistance to degradation by external factors such as alterations of temperature or light and moisture. So they are very sensitive and very delicate biomolecules. And because they are also highly volatile, they cannot be used in a free and loaded form. They can be used, for instance, for therapeutic actions on the skin, like ointments. The problem is if you use in formulations to treat infections, they are not as effective because they are so volatile. So our goal in this research was to engineer biodegradable microfibers treatment or microfiber strategy delivery platform to use to load these essential oils and then see their action on bacteria causing infections. Okay, so in this particular case, we use the wet spinning technique. For those of you that do not know, this wet spinning technique is a non-solvent phase inversion method in which we can produce continuous polymeric microfibers in with a uniform morphology. One of the most important effects of these wet spinning fibers, or one of the important properties, is the fact that we can create a structure, scaffolds with a larger porous structure than, for instance, we can use it with electrospinning. And electrospinning, even though they can create nanoscale fibers, they are not as effective in promoting cell infiltration. So we are looking at a different strategy here. This schematic representation of what we have here is basically what we are working in now in our lab. We are collecting the microfibers manually. However, we are already in discussions with the Department of Mechanics to generate an automatized system to collect the fibers so we can control it better, the formulation of these scaffolds. So in this particular study, we used 2 biodegradable polymers, which were both as well biocompatible. We selected the polycarpolactone, which mechanical performance is actually very desirable. And then we also used the cellulose acetate, because of the biological affinity. So these two polymers were combined in a ratio 3:1 of cellulose state and polycaprolactone respectively, and they were dissolved or prepared in solutions of acetic acid and acetone. As a coagulation bath, so we can produce the actual fibers, we used a non-solvent reagent, which was the ethanol. The fibers were extruded at a speed of 0.5 milliliters per hour within this coagulation bath. Regarding the essential oils, we selected them based on the literature. So we purchased 20 essential oils, the ones that we found the most literature about their antimicrobial potential to inhibit bacteria. And then we test them against the gram-positive bacteria, Staphylococcus aureus, and the gram-negative bacteria, Escherichia coli. The three most effective were the cinnamon leaf oil, the clove oil, and the cajeput oil. As a control antibiotic, we used the ampicillin, which is effective against these two bacteria. Regarding the essential oils, then we determined their minimum inhibitory concentrations. As you can see, they are a lot superior than that of ampicillin. This is not a discouraging factor, so we continue research because of that as well. What we realized is that when we put them together, we selected the cinnamon leaf oil just to see if, in fact, we had some effects on the bacteria. What we realized is that once we have the cinnamon leaf oil in contact with the bacteria, they were capable of disrupting the cell membrane of the bacteria, especially the Staphylococcus aureus. When it comes to the Escherichia coli, it was actually seen that the essential oil would surround the bacteria cells, preventing nutrient transfer. And then, I don't know if you can see by the images, but you start to look at the bacteria and you see some wrinkles being formed. So this means they start to be dehydrated, and ultimately they will die. So once we selected the essential oils and we had the fibers produced, so we started to immobilize the essential oils on the fibers. So for that we used a solution containing the essential oils dissolved or diluted in ethanol solution. So we could, since they are volatile, it's preferable to use this kind of solvent, and we used it at a concentration of 2 times mg. We used a little bit 2 times the minimum inhibitory concentration so that we could actually have an active immobilization on the surface. After we read the loading efficiency of the fibers, and we actually realized that even after 72 hours of immobilization, a period that was selected based on the ampicillin results, which reached 100% of immobilization after this period, which means the mg of ampicillin was loaded on the fibers, we actually realized that we only had 14% of the mg value for cinnamon, 66% for clove, and 76% for cajeput oils. So this is not exactly the 100% we are hoping for, but we have to compare with something. So we use the ampicillin as our control group, and they had to establish the same conditions. So what we realized here is the cajeput was effective, presented a superior affinity towards the fibers. So we had a larger percentage here immobilized. Then we looked at the effects of the fibers morphology, the immobilization of the oils, if it changed or not the morphology. What we realized is that the uniformity and homogeneous morphology of the fibers was maintained, and that the average diameter of the fibers was quite similar, ranging between 54 and 59 micrometers. Then, to confirm the presence of the oils along the fibers, we used the Fourier transformed infrared spectroscopy, and we actually noticed very small peaks, but visible peaks on the fibers containing the oils. And these 3 peaks corresponding to the aromatic ring CC skeleton vibration of the essential oils, or to the COH banding vibration of the alcohol moieties of essential oils, thus confirming the presence of the oils along the fibers. So the immobilization was in fact successful. Now, we studied the thermostability of these films and realized that the second and the third steps were actually very similar in behavior between all fibers, so the presence of the oils had no effect. However, if you look at the first step, we actually saw that there was a slight shift in the temperature, the gradation temperature, the beginning of the degradation of temperature from 150 and to 220 degrees. This is actually very interesting because we were expecting that the oils would volatilize completely in the first 100 degrees heating. And actually, we realized that this combination with the polymers was actually beneficial in protecting the essential oils for a little longer. So this is actually increasing the thermostability of the oils, this combination of these two polymers and these fibers. Then the most important data from our research was related to the antimicrobial action. This is actually we were trying to find out if we were capable of eliminating or at least reducing the presence of these microbial agents on the solutions. What we realize is that when they are in the free state, as expected, the antimicrobial action is more significant than when they are loaded. As you can see, they start to decrease the presence of the bacteria from the first moments of interaction, while when we have the presence of the fibers, we actually see an increase on the production or the growth of the bacteria in the first moments, and after that time, we actually start to look at a decrease of the number of bacteria. They have an action that is a little bit slower than we would expect. Then just to make sure that we compare these results or we related these results of the loaded fibers and the free agents. And we actually calculated the log reduction. So what we realize is that when they are free, we can reach log reductions of 3 and 4 after 6 hours and 24 hours. The same thing for Escherichia coli. But then when we look at the fibers loaded with the essential oils, we actually see that we can only reach at a log reduction of 2 at the 24 hours. And that happens both to Staphylococcus aureus and Escherichia coli. So they are not as effective as they are loaded. However, the most important or interesting feature here is that if you look at the results of ampicillin, which are the white bars here, and we compare with those of the essential oils, the results are quite close. And if you remember from the early results, we actually had the MIC value completely incorporated of ampicillin within the fibers. And in here we had a smaller percentage of the MIC value necessary to kill these bacteria from the essential oils. We think that the release of these essential oils from the fibers is superior to those of the ampicillin. So their action is improved. And we can actually see that growing here, now very close, and you actually see in the Escherichia coli that the cash-put functionalized fibers are actually more effective than the ampicillin. So these are very interesting and promising results. Then we actually, just to finish, we actually saw their ability of these essential oils and the ampicillin to permeate the cell membrane of the bacteria to see in which way they would act against these bacteria, and realize that once again the action of the antimicrobial agent was more effective against the gram-positive bacteria than the gram-negative. However, if you look again, the cash-put oil was more effective against the Escherichia coli, and for most cases, the cash-put oil is the most effective against the 2 microorganisms, even above the ampicillin. So these are very promising results. We are very looking forward to continue this research. So from what we gathered from this work, we realized that the microfibers were indeed uniform and homogeneous. We could successfully mobilize those fibers with essential oils. We actually saw that the oils were present along the fibers and that they were capable of transmitting a little bit more of thermostability to the polymeric blend, or vice versa. And then we saw that even at small amounts below MIC value, these essential oils could modify effectively the microfibers and promote cell death compared to the control groups, both unloaded fibers or modified fibers with ampicillin, and that they could disrupt the cell membrane by permeabilization of the microorganisms. So these results demonstrate that this effectiveness, this is just a small step that we are taking towards this research. We are still looking forward to continue this research and learn more about these essential oils and their mechanisms of action. For instance, we now are trying to use different polymers to bind the essential oils to the surface, to their surface, to see if their release can be mapped in a more controlled way. And we're actually developing now microcapsules where we can control by triggers the essential oils release, which is even more effective. So I just like to thank the groups that were involved. I didn't mention any people because we are a very small group, so we are always helping each other. And of course, the funding agencies and you for your attention. Thank you.
Well, thanks a lot for your presentation.
For your nice presentation. We have time for some questions.
Yes. So you can ask your questions on the YouTube page or directly from here. Any questions? ¿Alguna pregunta? Creo que no tenemos preguntas.
No.
Vamos a ver.
Ok, então, muito obrigada por me terem e até a próxima.
Thank you very much.
Obrigada.
Gracias.
Ok, continuamos con la siguiente charla entonces. ¿Sí?
Sí, podemos.
Sí, adelante.
Ok, continuamos entonces con la charla que nos presentará Débora Karina González de la Universidad del Niño, Portugal, titulada Peptide Mediated Target Delivery System Towards Triple Negative Breast Cancer Treatment.
So, good morning to everyone. My name is Débora Ferreira and I'm a PhD student from University of Minho, Portugal. And I'm here to present my work related to my PhD thesis named Peptide-Mediated Targeted Delivery System Towards Triple-Negative Breast Cancer Treatment. So, triple-negative breast cancer occurs in about 10 to 20% of all diagnosed breast cancer cases and is more likely to affect younger people, African Americans, and Hispanics. It is also the most aggressive subtype of invasive breast cancer with a poor prognosis. In triple-negative breast cancer, none of the three important receptors, HER2, progesterone, and estrogen, are found on the cell surface. This makes it difficult to use the conventional treatments as surgical intervention, radiation, and chemotherapy. However, these conventional treatments have also some drawbacks, including non-specificity, non-selectivity, and also high cytotoxicity. Due to its unique profile, aggressive behavior, and different patterns of metastasis, the search for effective diagnosis and treatment tools has intensified. To do so, the search for new tumor biomarkers is the first step to reach early detection and an attempt treatment. A tumor biomarker could be proteins, DNA, RNA, membrane receptor, cancer cells, among others. They are quantifiable from bodies, fluids, or mass samples. Normally, they are overexpressed in a tumor mass, and they could also be correlated with disease stage and progression and also patient's outcome. However, the lack of specific cell targeting remains the main barrier for the development of these sensitive diagnostic and treatment tools. Therefore, peptide ligands that specifically recognize cell surface receptors have been extensively used in cancer research. So, these engineered bacteriophages could help in diagnosing and use as a treatment tool for cancer, since they can help identify new targeted sequences towards cancer cells. To do that, they could be modified in their surface to bind to possible targets of interest. This includes the evolutionary screening techniques as phage display that emerges as a powerful tool to recognize specific peptides and has been proven useful for discovery of new biomarkers. So this phage display technology is a selection methodology that favors the enrichment of specific binders from an initial library that leads to the identification of new target sequences that specifically recognize the cancer cells, and then to the correspondent identification of the target by reverse genetics and bioinformatic tools. The phage display is really useful for the development and for the discovery of novel targets for cancer diagnosis and treatment. So this technique has been highly successful in generating peptide ligands against a large variety of novel targets concerning solid tumors and the tumor niche, both in vitro and in vivo, and revealing the overall strength of this methodology to personalize targeted cancer treatment. So here we have in a scheme a normal protocol of phage display that starts with incubation of phage display library with the target cells, and after target exposure the unbound phages were washed away and the bound ones eluted for phage amplification in bacteria. After these phage amplified in bacteria will be incubated again with target cells for another round of selection. After several rounds, the amplified phages were sequenced, and a subset of phages presenting higher affinity to the cell target were used for binding assays, and in the end, the peptides will be identified by bioinformatics. In the end, we will have peptides with relevant clinical application. So we use this technique for the identification of novel peptides, identifying and homing the 41 cells. The 41 memory adenocarcinoma murine cell line has presented itself as a good model system as it closely resembles the human TNBC. So the identified peptides were characterized and their binding specificity towards this cell line was confirmed either by immunofluorescence and by flow cytometry. The phage particles displaying the selected peptides, the 41PEP1 and 41PEP2, were applied to these 41 sections, and the wild-type phage was used as a negative control. Both peptides identified by this phage display were able to bind efficiently to the 41, as we can observe here by the green spots highlighted by the white arrows. Moreover, the high selectivity of the 41 cell line targeting peptides was confirmed by flow cytometry. As we can observe here, about 70% of the overall cell population was bound to the 41PEP1 and about 60% was bound to 41PEP2. Furthermore, no positive binding was found when the peptides were incubated with the T3 cell line, proving the specificity and affinity of the selected peptides. Then, given the great affinity of this kind of peptides for triple-negative breast cancer cells, we decide to equip exosomes with these ligands to confer them more specificity and more affinity for the triple-negative breast cancer cells, and then use them as drug delivery vehicles. But what are exosomes? Exosomes are extracellular vesicles ranging from 40 to 150 nanometers that are generated by all cells and exchanged between them. Exosomes are typically characterized by their size and also by the expression of common marker proteins, including tetraspanins, the CD9, CD81, and CD63, flotilin-1, integrins, the major histocompatibility complex, short proteins, ALEX, TCG 101, and also contain other proteins, different species of RNA and DNA. Therefore, they are often used to deliver a therapeutic cargo for treatment. That is the goal that we want to accomplish. The exosomes that have been used include both natural ones without any kind of genetic engineering or chemical engineering, and also those that have been modified with other substances, other molecules, to increase the delivery ability. Then we collect exosomes that were derived from the BJ cells that are fibroblasts, and they were isolated by differential centrifugation, and they are then further characterized by flow cytometry and also by their size. As we can observe here, the mean size of exosomes were 109 nanometers. We have here a TEM image proving that we have exosomes in the solution, and then we characterize by either Western blot and by this flow cytometry the presence of the common markers, the common tetraspanins that I referred previously, the CD9, CD63, and the CD81. Here in this flow cytometry graphics, in the red are represented the beads without exosomes, and at blue the beads conjugated with exosomes. Then we studied the uptake of these isolated exosomes by MDA-MB231 cells that are triple negative breast cancer cells. And as we can observe here on the left and represented the red, the exosomes are uptake by these cells. And here we have a video the exosomes are represented orange. And this is a 24 hours uptake experiment using a time-lapse microscopy. And as we can see, the exosomes were uptake by cells. So then we did an assessment of the in vivo biodistribution of these exosomes, and to do so we labeled them using a lipophilic dye, the DAR, and they were IV injected in healthy mice. Then we did the tissue biodistribution were assessed using an IV system. The DIR only were used as a control, and as we can observe here, the DIR labeled exosomes accumulate beta in liver, lung, and spleen when compared with only DIR. Then the tissues were collected and processed, and the organs that had the bigger signal in the IVIS machine were the ones that also have signal in this confocal imaging, as we can see here in liver, represented at these red spots, at lung, and also on spleen, and not in heart, brain, and pancreas, as we see in the previous images. Could also be interesting to study in which organ subpopulations these exosomes are accumulating beta. These cell-derived exosomes have been demonstrated to be efficient carriers of therapeutics, of drugs. However, their cell specificity and biological effects can be unpredictable. So, to overcome this limitation, we want to equip these cell-derived exosomes, and we are doing some efforts in engineering these exosomes with the targeting ligands that I already explained to you. We aim to introduce those peptides onto exosomes using a PEG micellar post-insertion strategy that is here presented. And afterwards, we will perform size exclusion chromatography to obtain the pure fraction of engineered exosomes. And we will use the conventional techniques to characterize them as nanoparticle tracking analysis, TEM, flow cytometry, and Western blot. So we have some further work. We want to do some cell binding experiments with the breast cancer cell lines to be sure that the modified exosomes actually leads to an improved uptake when compared with non-modified ones. We also want to do in vivo circulation times and biodistribution experiments to compare the performance of modified and non-modified ones. and also to do the same experiments in tumor models. And we hope that these modified exosomes accumulate better on the tumor sites. And also do and studied in vivo behavior of the peptide target exosomes incorporated with drug molecules. So the last remarks of my presentation is that peptides can be either used to develop diagnosis solution or targeted drug delivery therapeutics, and also that exosomes comprise a useful nano-based solution to be further used in gene therapy. These targeted exosomes open a completely new paradigm for the therapeutic delivery of drug molecules to specific targets, and opening also the door for new treatments of diseases caused by the aberrant gene expression as cancer. Thank you for your attention, and if you have any further questions, please feel free to ask.
Sí, continúa, Carla.
Well, thank you very much for your presentation.
Thank you.
Obrigada pela presentação. Preguntas, estamos esperando sus preguntas. Está abierto el link de YouTube y también pueden hacerlo directamente por Zoom. Así que si alguien tiene alguna pregunta. Creo que no tenemos preguntas hasta el momento. No.
¿Por YouTube tampoco? ¿Consultas?
No tenemos preguntas. Muchas gracias por la presentación.
Thank you for the invitation. And if you have any question, you can always contact me. Okay? Thank you.
Vamos a dejar el correo para que si alguien tiene dudas se sienta libre de hacer todas sus preguntas. Yeah. Muchas gracias.
Yeah, thank you.
Bueno, entonces continuamos con la siguiente charla que nos presentará Luis Almeida de la Universidad de Minho, en Portugal, titulada Risk Management of Nanomaterials Case Study in the Textile Industry. Gracias, Luis.
Buenos días, aquí en Portugal, buenas tardes. Espero que me están oyendo, ¿sí? Necesitaría
sí, sí, no hay problema, se escucha bien.
Mi pantalla.
¿Puede compartir su presentación? Ahí sí.
¿Está bien? ¿Están viendo?
Sí.
Bueno,
sí.
La presentación va a ser en inglés, o sea, vamos a empezar. Tenemos, bueno, this work, risk management of nanomaterials, case study in the textile industry. Yes, this work has been done in collaboration with the first president, in fact, is Dr. Defino Ramos from the Polytechnic Institute of Porto. And it has been done in collaboration with a textile company. So this is a brief outline of the presentation. So we'll speak about the control banding process, textile finishing, and the results involving two nano finishes. Due to the limitation of time, I will only speak of one of the products and then a conclusion. So nanomaterials have unique chemical, physical, and mechanical and biological properties. There are already in the market many consumer products with nano, including garments and textiles. One of the characteristics is that they may be more readily absorbed or overcome the physiological barriers of the body, and so the regulating authorities have started to put more emphasis on the potential risks for human health. So we have the exposure for the workers and for the consumers and also for the environment. In this presentation, we will consider mainly the health and safety aspect for the workers involved in textile processing. So the hazards or source of risks can be related to inhalation, absorption to the skin, or skin or eye contact. I'm entering not in too much detail. And what can we do? We can, in terms of risk management, we can isolate or enclose operations where the nanomaterials are used, have engineering control measures, administrative control, or at the end, if another of the rest is possible, is to use the personal protective equipment. It is important, of course, to know if the chemicals you are using incorporate nanomaterials. There are advantages and inconveniences of nano. So some of the producers say for marketing that they are nano, others on the other hand, they hide that they have nano. And so there are not yet regulations that impose that you have to say that you have nano in the materials. So here are some of the nano materials that can be used in textile finishing. In the work we have done includes mainly silver nanoparticles and silicon dioxide nanoparticles. I won't enter into detail about So the control banding. This is a technique that has been originally developed by the pharmaceutical industry as a way to safely work with the new chemicals that had little or no toxicity information. So it's a pragmatic approach to control of the workplace exposure to possible hazardous agents, for which you don't know yet the toxicological properties. And this is, of course, the case of nanomaterials. That's why within ISO, there's been a technical specification developed already in 2014, which is use of control banding approach in occupational risk management applied to engineered nanomaterials. It is interesting techniques for this kind of materials. So the standard, this is a schematic of the standard. You have to have the product information as far as possible, and according to the product information, you have a hazard band. And then from the exposure information, depending on the workplace exposure, you define the exposure band setting, and gathering both, you have the control band technique. Then afterwards, you can have a periodical reassessment of the risk banding. So very briefly so we have used a process of proactive process in this study. And so this includes also the possibility of the propensity of the material to become airborne, and also the quantity of the material that is being handled. So according to ISO, these are the 5 hazard bands from A, no significant risk to health, until E, significant hazard. We will see that materials we have used go up to hazard band C. Then the exposure banding, the standard presents 4 levels from EB1 to EB4. And this is, we have used in our case only EB1 and EB2 because the materials are used in a suspension in a liquid. And at the previous slide I have shown you, we combine the hazard band and buzzer of exposure, and you have the control band, which is within this matrix from CB1 to CB5. Yeah, and the measures to be taken into account for these five control bands come just from the simple natural mechanical ventilation, local ventilation, enclosed ventilation, up to full containment. So, as we have said, we present a case study in the textile finishing company. It's a company that finishes mainly knitted fabrics. And for certain customers, they ask for finishes that incorporate nanomaterials. And this, we have studied these 2, mosquito repellent and antibacterial finish. As the antibacterial is more harmful according to the safety data sheet. So here are the hazards concerning the antibacterial product. As you can see, there are some aspects that can be considered as relatively hazardous. And so we, but none of these products, the anti-mosquito and the antibacterial, present in the safety data sheets information that they are nano, although the suppliers said, but they say that the remaining composition of the product is kept secret by the company. So we didn't have so much information about the chemicals, but we made a study. And the two chemicals are applied to cotton fabrics by padding, followed by heat setting at the center frame. So this is the main machine used in textile finishing. And we considered 4 workers that are involved in either in the manipulation of the preparation of the baths, so coming from the warehouse until the machine. And the chemicals are delivered in cans in suspension or aqueous forms, which is an advantage in terms of exposure. So what do the 4 workers do in terms of manipulating? Opening of the cans, weighing, transportation of the chemicals to the production process, transfer to the center frame, although there is an automatic expansion, so not so much exposure, then preparation with water addition, and the process of conducting the machine itself. And for product B, so I said we are considering product B because more harmful in this presentation. So for these 4 tasks, we have hazard bands C for all, and exposure bands 2 or 1, in a production only 1, and the control band means CB3. So it's, remember there is from CB1 to CB3, which is a medium control band. So why do you choose C? Because it's a chemical that can cause serious eye irritation as well as other health problems, and exposure bands 2 because it is a suspension form, so low potential for aerosol formation, but it is used in quantities higher than 1 liter. This is what is indicated in the standard. In the production, there is not so much exposure. So this means that there is CB3, which means that you have to have closed ventilation, ventilated booth, fume hood, closed reactor with regular opening, and for the center frame, less measures are not so strong. So what the company has done, they have, according to the safety data sheets, they use the PPE, protective glasses, nitrile rubber gloves, protective clothing, respiratory protection masks when vapors are released, but there are still other measures, namely in CB3, that are still not used, namely closed reactor with the opening of the can. So, as a conclusion, not to take too much time because we are delayed, there are within this control band technique, there are we suggest some control measures for risk mitigations by use of this technique, and the company should carry more in detail this study, namely exposure measurements in the workplace. The main problem we have faced is the lack of information from the products used in the safety data sheets. They don't say too much about the hazards and risk of nanomaterials. And there is a new REACH in Europe, REACH registration system, which starting from January this year, January 2020, you have to have a special registration with nanomaterials, and you have to give more information. So this is a technical report published by ISO, nanomaterials, preparation of material safety data sheet, which can be interesting for this study. So this is very briefly my presentation, because I know you are delayed, so I didn't want to take you too much time. But if there is still some time for questions, I'm free. Otherwise, you can always contact me or the Prime Doctor, Dr. Afina Ramos. We have sent a small abstract, which with all the contacts. Okay, thank you.
Okay, thank you very much for your presentation. It was very good and very notative. So now we have
pueden poner las preguntas en castellano, en portugués o en inglés. Todo va bien.
Muy bien, entonces.
Sí.
Estamos esperando entonces las preguntas por... Aquí hay una de Delfina Gabriela Garrido Ramos que pregunta, o sea, que dice: parabéns, professor Luiz Almeida, pela excelente apresentação do nosso trabalho de investigação. Congratulations for the excellent presentation. Después, Diana Silva Avila dice, very interesting assessment. Thank you for this presentation. Was any biomarker evaluated in this work? Red blood cells or white cells analysis, for example?
Can you repeat? ¿Puede repetir?
Was any biomarker evaluated in this work? Red blood cells or white cell analysis, for example?
No. As I said, we only made the study according to the safety data sheets. But one of the suggestions to the company is that she should make a more detailed study about the workers. But we did not make any more study. Just was according to what is performed in the machines, and then according to the safety data sheet. We did not make any study for the moment. Okay.
Okay, thank you very
much. But this is a suggestion we gave to the company. Of course, in this moment it's very complicated because companies have reduced the production. They have not so much money, so to invest in these things is not so easy. But it's a suggestion that we have put to the company. Okay.
Okay, thank you very much. Is there another question? Si tenemos alguna otra pregunta. Aquí. Os trabalhadores mencionaram algum desconforto ou efeitos na saúde?
No. No ha sido encontrado hasta ahora. Bueno, primera cosa, los trabajadores no saben, porque es mucho poco divulgado la manipulación de nanopartículas. O sea, no tienen ninguna información particular respecto a nano o respecto a otros acabados. Porque esos trabajadores, la compañía algunas veces emplea nano, la mayor parte de las veces no emplea nano. O sea, no ha habido ningún problema hasta ahora.
Sí. Ok, muchas gracias.
La persona que ha acompañado este trabajo en la empresa es el responsable por la parte de higiene y salud en el trabajo, y eso sí está naturalmente muy interesado en este estudio, pero hasta el momento no se ha encontrado ningún problema en estos trabajadores. Como he dicho, solamente 4. ¿Sí?
Muchas gracias. ¿Hay más preguntas? Creo que no tenemos más preguntas por ahora.
Muchas gracias. Le agradezco la invitación para participar en esta conferencia. Pienso que esta tarde esta mañana muchas personas de Portugal. Gracias. Saludos.
Muchas gracias por la presentación.
Muy bien, entonces a continuación vamos a seguir con esta jornada. Que seguirá va a ser Diana Andrade Sousa, de la Universidad de Minho, Portugal, que nos va a presentar el trabajo titulado Targeting Oncogenic MacroRNAs in Triple-Negative Breast Cancer using a CS9-based approach. You can start.
Good morning. My name is Diana Souza, and I'm a PhD student from doctoral program of Bioengineering Systems from University of Minho. My PhD work is focused on the development of triple-negative breast cancer therapies, more properly in targeting oncogenic microRNAs present in triple-negative breast cancer using a CRISPR-Cas9-based approach. Triple-negative breast cancer subtype is responsible for 15 to 20% of all diagnosed breast cancer, so 2 out of every 10 cases, and it is characterized by the lack of human epidermal receptor 2 and estrogen and progesterone receptors. Treatment options for TNBC patients are limited, and surgery, chemotherapy, and radiotherapy are the main treatment options. Due to the lack of effective therapies, new interest has emerged on identifying new molecular targets to improve the TNBC patient survival and prognosis. In the recent years, numerous publications have highlighted the role of microRNAs in the regulations of gene expressions And some microRNAs have been associated with tumor initiation and tumor progression, being termed as oncogenic microRNAs. MicroRNA 155 is one of the most upregulated microRNAs in different types of cancers and has been associated with breast cancer progression, metastasis proliferation, and drug resistance. And for that reason is a microRNA selected for this study. Many methods have been developed for microRNA losing function, such as antisense nucleotides and inhibitors, sponges, but the specificity and the stability of these strategies are not fully satisfied. The design of CRISPR-Cas9 systems to target specific microRNAs has emerged as a cancer therapeutic approach because CRISPR-Cas9 is a highly precise genome editing tool, and it is a system easy to design and has been reported as a more effective, specific, economic, and stable technology for knocking down microRNAs. Regarding to the delivery of CRISPR-Cas9 systems, two approaches have been used, the viral and the non-viral. The viral approaches had a good performance on the delivery of the Cas9 systems, but they are limited by the packing capacity and the immunogenicity. The non-viral delivery methods have the potential to overcome the limitations of the viral approaches with safety, large packing capacity, and good results in the in vivo applications. So the main goal of this project is the construction of CRISPR-Cas9 genome editing systems against microRNA 155 using a targeted lipids nanoparticle for TNBC therapy. So firstly, I construct CRISPR-Cas9 systems against microRNA 155. Then I validate the constructions in a TNBC cell. The constructions have been encapsulated into liposomal delivery systems, and then these liposomes will be functionalized with specific ligands for TNBC cells in order to improve the delivery efficiency. So for the construction of a CRISPR-Cas9 systems to target microRNA 155, two single-guide RNAs sequence were designed through ChopChop informatic web tool. And thereof targets were predicted by bioinformatic blasts using a CC-TOPE CRISPR-Cas9 target online predictor. The present table shows the on and off target sequence obtained for each single guide RNA. And these guide RNAs were cloned into a CRISPR plasmid through Golden Gate cloning strategy. The PX459 plasmid was digested using PBS1 enzyme, and the annealed single guide RNAs was inserted into the plasmids. To choose the cell model to use, the expression of microRNA 155 was studied in a panel of TNBC cell lines by real-time quantitative polymerase chain reaction, and AJAS 578T cell line was selected as the cell line model due to the significantly elevated levels of this microRNA in the cell. Genomic DNA from transfected cells with Cas9 plasmid containing the designed single-guide RNA was amplified with specific primers for on-target and for off-target sites, and the PCR products were subjected to T7 endonuclease 1 assay. The T-set endonuclease digestance allows recognize and cleaves the genomic DNA whose genome we're editing using the Cas9, and we can detect in both single guide RNA the cleavage in the DNA. Also, regarding the off-targets, single guide RNA 2 proved to be more specific than single guide RNA 1, which show the existence of cleavage DNA in the off-target 1 and in the off-target 2. Despite of the genome editing efficiency of CRISPR-Cas9, the transfection is one of the most critical step for the use of this technology due to the large size of the DNA plasmids. Microscopy and cytometry results show the transfection efficiency of PX458 plasmids into TNBC cell line using a commercial cationic lipid reagent after 48 hours of incubation. And the transfection results in less than 20% of GFP positive cells. So the transfection efficiency is very low. For that reason, emerged the need of a CRISPR-Cas9 delivery solution to improve the transfection efficiency. Liposmall combinations of a cationic lipid, DOTAP, and a neutral lipid, DOPE or DOPC, was tested with different ratio, 80-20 and 30-70, and different proportions of liposomes and DNA were also tested, the charge ratio 3 and the charge ratio 10. Fluorescence cross-correlation spectroscopy was performed to evaluate the DNA complexing ability of the liposomes. This technique is used to provide a dynamic co-localization of two objects labeled with different color dyes through the fluorescence emission intensity. It is possible to observe that the formulation 80-20.APC for both charge ratios show better DNA complexing. These formulations were also used for fluorescence microscopy assays to evaluate the cellular uptake ability, where we can see a great internalization of DNA in the cells and accumulation near to the nucleus. FCCS was also performed to DOTAP-DOPC formulations. In this case, the conditions with charge ratio 3 show better DNA complexing results, however lower than the ones with DOTAP-DOPC. In the fluorescence microscopy images, it is possible to verify a higher fluorescence intensity in the 80-20 DOTAP-DOPC formulation compared to the 30-70. Nevertheless, the DOTAP-DOPC formulation demonstrates better results of cellular uptake. The toxicity effects of these lipoplexes were evaluated by MTT assay after 24 and 48 hours transfection. It is reported that the lipoplex cytotoxicity is closely associated with the charge ratio between the cationic lipid and the DNA. And in this graph, it is possible to observe that the higher charge ratio decrease the cell viability in the most of the liposomal formulations tested. As final remarks, through the obtained result, it is possible to affirm that in silico tools to design single guide RNA are the key for high specificity to on-target loci, and the evaluation of target effects is relevant to develop highly precise genome editing systems as a treatment platform. The single guide RNA2 for microRNA 155 seems to be a good candidate for TNBC treatment, due to the high on-target specificity and the low target effects. And regarding to the preliminary results of delivery systems for CRISPR-Cas9 plasmids, cationic lipid formulations of DOTAP-DOPE and DOTAP-DOPEC seems to be a useful nano-based solution to use in gene therapy. So thank you for your attention.
Thank you very much for your presentation. It's a very interesting topic. We have some minutes for some questions.
Yes, the links are open for any question you have. So. Okay, aquí Marcela Sorelli says, congratulations, Diana. Have you ever performed some experiments in vivo? Diana? Hello, Diana. I think your speaker is silent.
Can you repeat the question, please?
Have you ever performed some experiments in vivo?
No, not yet. But I will perform in the next months.
Okay, thank you very much. This question was from Marcela Sorelli. Are there other questions? I think we don't have any more questions.
Okay, thank you for the opportunity to present my work here.
Thanks to you for your great presentation.
Thank you.
Ok, continuamos con la siguiente entonces. ¿Sí? Ok.
Sí,
vamos
adelante.
ahora entonces con María Georgina Sander, ¿sí? De la Universidad de Minho, Portugal, con la charla titulada Collagen Coat Magnetic Nanoparticles to Capture Pathogens from Biological Samples.
Good morning. My name is Maria Sandy, and I'm presenting this work on behalf of my colleagues and myself, titled Collagen-Coated Magnetic Nanoparticles to Capture Pathogens from Biological Samples. This work was performed as part of the Viral and Bacterial Adhesion Network Training, or VIBRANT, which is an innovative training network funded by the Marie Curie Actions. The focus of VIBRANT is the adhesion of pathogens to human cells. This is because adhesion is thought to play an important role in the infection process. By studying adhesions, it can lead to new understanding of infections, new diagnostics and devices, and eventually new treatments. The conventional methods of diagnosis include microbial culture and more modern methods such as PCR, next-generation sequencing, and mass spectrometry. While these methods are reliable and highly sensitive, some disadvantages can be that they are very sophisticated. They are expensive, they need skilled operators, and some methods like culturing is time-consuming. The target pathogenic bacteria also often exist in complex samples and in very low concentration. This necessitates processing of the samples before diagnosis. So there is a need for affordable, easy-to-use diagnostic methods with enrichment of bacteria present in the sample could be a diagnostic approach. It is known that bacterial infection is started by colonization of the host. For this purpose, bacteria express proteins on their outer surface called adhesins, which are able to recognize specific host molecules. And collagen is one such host protein recognized by these adhesins. This adhesin-collagen interaction can be mimicked in vitro and serve as a method for bacterial enrichment. The objective of the work is to demonstrate the enrichment of bacteria by collagen-coated magnetic nanoparticles. First, the magnetic nanoparticles are synthesized and functionalized with collagen, and next they are characterized. Parallelly, bacterial cloning is used to express adhesins recombinantly on the surface of bacteria. Finally, these two elements are used in adhesin assays to demonstrate bacterial enrichment. The collagen-coated magnetic nanoparticles were synthesized chemically. They were characterized by Fourier transform infrared spectroscopy and dynamic light scattering. YARD-A, an adhesin from Yersinia enterocolytica, which is a pathogen, and a reporter gene GFP were cloned into a lab strain E. coli. Similarly, USPA2, an adhesin from the pathogen Moraxella catarrhalis, along with a red reporter gene M-cherry, were similarly cloned into E. coli strain of bacteria. Next, the bacteria were grown and the expression of the YARD-A and GFP induced. Similarly, the USPA2 and M-cherry were induced and expressed. Some co-culture experiments were also planned, and for this, co-cultures were prepared by simply mixing the two cultures and growing it from an OD of 0.5. For the bacterial capture experiments, the collagen-coated magnetic nanoparticles were incubated with the bacteria for 3 hours to promote binding. Next, they were separated by a magnet and the supernatant collected, which had the non-captured bacteria. They were then resuspended in PBS and again separated by a magnet, and the supernatant was again collected. The separated bacteria and magnetic nanoparticles were taken for confocal microscopy, and the capture concentrations were used to calculate the capture efficacy. The results of the FTIR, the spectra confirm the presence of collagen. As you can see that the characteristic peaks of collagen are present, as well as the iron oxide peaks. We tested variations in the collagen concentration and functionalization pH on the diameter and zeta potential of the nanoparticles. Zeta potential is an indicator of stability of the particles. Finally, nanoparticles with a collagen ratio of 0.7% at a pH of 7, which is physiological pH, and a diameter of around 240 nanometers and zeta potential of 18.2 millivolts was selected. Both adhesins were able to capture bacteria as compared to the negative control, with the USP2s faring slightly better than the YARD-A. The results from the confocal microscopy perhaps best demonstrate that the adhesion between the bacteria and the collagen nanoparticles. In the first set of images, we see the green YARD-A has been captured by the collagen nanoparticles. In the co-culture microscopy, it appears that the green Yade and the red USPA2 were equally successful in competing for capture by the nanoparticles. So in conclusion, the pre-enrichment of bacteria by two types of adhesins was demonstrated, and the capture efficacy of the two was also calculated. For Yade, it was around 50% capture efficacy, and for USPA2, around 68%. In the next step, perhaps enrichment of bacteria from real samples, such as patient blood or urine, can be used to demonstrate pre-enrichment. Future perspectives. Pre-enrichment of pathogens from samples can be combined with subsequent steps such as bacterial identification and detection steps, and together they could possibly form an integrated diagnostic system. Bacterial pre-enrichment methods as described in this work have the potential to be affordable and simple, yet highly effective as diagnostic methods. Thank you for listening.
Thanks a lot for your presentation. It was very good and very entertaining. So I have time for some questions.
Hi. Thank you. Thank you for the opportunity. Yes, if you have any questions, please go ahead.
Thanks to you for your presentation. So we are open for questions. If there's any doubt. Okay, so Marcela Sorelli asked, great Maria, which kind of collagen?
What kind of collagen I use? For these experiments, we purchased commercially available collagen, and it is bovine collagen from pigs.
Okay, thank you.
If that's the answer she wanted.
Yes, I think so.
Okay.
The question was from Marcela. So, yeah, she said, okay, thank you.
Okay.
So we're fine. Okay, so any question? Well, thanks for your presentation. And I think we don't have any more questions here.
Okay, thank you very much. Goodbye.
Okay.
Thank you.
A continuación voy a presentar al siguiente conferencista de esta jornada, Andrés Sampaio Ferreira, de la Universidad Estadual de Londrina, Brasil, que nos presentará el trabajo Effects of Nitric Oxide Donors and Gibberellic Acid Loaded Chitosan Nanoparticles on Mice Germination Performance Under Thermal Stress. Thank you. You can start, please.
Hello, everyone. Do you hear me?
Yes, of course.
Okay. Do you see my presentation?
Yes.
Okay. Well, my name is Andrés Sampaio Ferreira. I'm a member of Dr. Halley team at Londrina State University. And I'm making a presentation.
Hay un problema con el audio, André, parece. No sé si yo no escucho. No
André, aqui para mim não deu para escutar. Confira só o seu som, o seu áudio, por favor.
El volumen.
Sim, o volume.
Porque al parecer el micrófono está conectado. No.
Então,
Eu estou logado também pelo um outro perfil aqui. Estão escutando agora?
Agora sim, André.
E a apresentação tá aparecendo também?
Tá naquela do Mapa Mundi.
Tá, tudo bem.
Bom?
É que eu estou logado no celular e no computador.
Ah, então, entendi. Tá.
É bom que eu estava no celular também. So I made my presentation again. My name is André Sampaio Ferreira. I'm a member of Dr. Ale Caixeta de Oliveira team at Londrina State University. My work is effects of nitric oxide donor and gibberellic acid-loaded chitosan nanoparticles on maize germination performance under thermal stress. So I made my presentation in Portuguese. Sorry for this. Ok? Então, esse trabalho ainda está em execução por conta das condições da pandemia. Então, nós trouxemos alguns resultados preliminares, tá? E mais para apresentar o projeto mesmo. Bom, o milho é uma das principais culturas alimentares do mundo, tá? Alimenta basicamente boa parte da população mundial, é produzida em quase todas as partes do mundo, tá? Só deixa eu mudar aqui o ponteiro. Então, veja que o milho é produzido em quase todas as partes do mundo, sendo que o Brasil, atualmente, é o terceiro maior produtor de milho. Então, veja toda a área de produção de milho aqui no Brasil, tá? Sendo os Estados Unidos os maiores produtores. Dessa forma, qualquer estratégia de manejo que possa elevar a produtividade ou a estabilidade produtiva do milho é de interesse mundial. Bom, no sistema produtivo do milho, temos alguns momentos de maior suscetibilidade a estresse e momentos críticos para a construção da produtividade. Dessa forma, o período da germinação e emergência é um período crítico para a construção da produtividade, pois nesse momento estamos definindo o número de plantas por unidade diária, de forma que se houver algum problema nesse estágio, é possível que tenha menor plantas por unidade diária do que o esperado, e isso resulte em menor produção. Nesse momento, a ocorrência de estresses abióticos, como calor ou frio no solo, pode reduzir a uniformidade de emergência. Então, aqui é um exemplo claro de plantas que emergiram atrasadas em relação às demais. Tá? Aqui também pode-se ver uma planta atrasada. Isso é muito prejudicial em lavoura de milho, especificamente. Tá? É uma planta que não tem capacidades para compensar essa desuniformidade aqui, de forma que essas plantas que emergiram primeiro acabam dominando as vizinhas e ocorre redução da produção. Bom, nesse processo, então, tão importante que é da germinação e a emergência, estabelecimento da lavoura, já é conhecido o efeito de um hormônio vegetal, né, um grupo de hormônios, do grupo das giberelinas, sobretudo o ácido giberélico, que atua nesse momento da germinação, tá? Então, esse hormônio ele é produzido pelo embrião, e o embrião, então, libera esse hormônio que vai ativar a camada de aleurona, que é uma camada que é responsável pela síntese das enzimas que vão atuar na degradação do amido, que está armazenado no endosperma do grão, e esse amido, então, vai ser quebrado em açúcares menores, que vão ser utilizados como fonte energética para que a semente possa restabelecer o seu metabolismo e fazer o seu processo de germinação, tá? Então, em teoria, se eu fizer um tratamento de sementes com ácido giberélico, eu poderia melhorar o desempenho germinativo da planta, sobretudo em condições de estresse. Entretanto, na prática, nem sempre isso acontece. Então, os resultados são um pouco divergentes em relação a isso. Então, a nossa pergunta científica é: a nanotecnologia pode aumentar a eficiência dessa aplicação? Bom, além da questão da germinação e emergência em relação aos hormônios, muitos outros fatores também afetam o estabelecimento de plantas na lavoura, tá? Então, fatores genéticos, da qualidade da semente e do ambiente, tá? Aqui no ambiente, temos um caso em que baixa temperatura de solo pode, então, reduzir o estande de plantas, tá? Ocasionando essas falhas e redução de produtividade. A nossa estratégia, então, é atuar nessa qualidade da semente, ou na qualidade do material. Por quê? Além do ácido giberélico, nós estamos estudando moléculas doadoras de óxido nítrico. Então, esse óxido nítrico, a literatura já tem demonstrado que quando as plantas se encontram em situações estressantes, o óxido nítrico exerce um papel importante na sinalização, né, eliminação de espécies reativas de oxigênio e outra interação com hormônios, para aumentar a tolerância ao estresse. Entretanto, essas partículas, esses doadores de óxido nítrico são muito instáveis, e a aplicação deles em campo seria inviável, porque a meia-vida deles é de alguns segundos. Então, a nossa ideia é que com a nanoencapsulação desses doadores, se possa ter uma liberação mais controlada desses doadores de NO, e com isso, então, prolongar o efeito protetor, aumentando a tolerância ao estresse. Então, nossa segunda pergunta é: pode a nanotecnologia aumentar a estabilidade do doador de NO e permitir, então, uma liberação controlada, aumentando a tolerância do milho ao estresse térmico? Bom, de maneira simples, eu coloquei aqui o que nós fizemos no nosso experimento. Então, nós pegamos sementes de milho, fizemos uma embebição com os tratamentos, né, de interesse, por aproximadamente 6 a 8 horas. A partir do momento que a semente absorveu todo aquele conteúdo, nós colocamos elas para germinar em papéis de germinação e avaliamos, então, o desempenho germinativo dessas sementes em 3 temperaturas. Temperatura baixa, temperatura ideal e temperatura alta, tá? Simulando, então, o estresse por baixa e alta temperatura, que é comum em condições de lavoura. Então, aqui estou apresentando dados de 2 experimentos. Um experimento com ácido giberélico, em que avaliamos um controle com água destilada, o ácido giberélico, as nanopartículas de quitosano e alginato vazias e as nanopartículas contendo o ácido giberélico, em 3 concentrações e nas 3 temperaturas. De maneira semelhante, o trabalho com óxido nítrico, avaliamos também um controle, e aí 3 concentrações de um doador de NO livre, da nanopartícula de quitosana vazia, e da nanopartícula contendo o doador, também em 3 temperaturas. Bom, os nossos resultados preliminares aqui em relação ao ácido giberélico, olhando aqui então, temos as 3 barrinhas em verde indicando as 3 concentrações do ácido giberélico isolado, as 3 barrinhas em vermelho indicando as concentrações da nanopartícula vazia, e as 3 barrinhas em azuis indicando a nanopartícula carregada. Então, esse padrão segue para toda a apresentação. Bom, na baixa temperatura, não tivemos grandes influências dos tratamentos sobre a porcentagem de germinação, também na temperatura normal. Em contrapartida, na alta temperatura, tivemos uma influência bastante significante, tanto da aplicação do GA3 isolado, quanto das nanopartículas isoladas e da nanopartícula contendo o GA3. Em relação ao experimento de óxido nítrico, vimos aqui, na baixa temperatura, influência do doador livre, da nanopartícula isolada, aumentando a germinação. Na temperatura normal, ausência de resposta, como esperávamos para esse experimento, haja visto que não tem muito estresse nessa situação. E na alta temperatura, as maiores respostas, indicando o efeito tanto do doador livre, quanto da nanopartícula, quanto do doador nanoencapsulado. Aqui é importante frisar que esse experimento ele é conduzido num laboratório, numa câmara de germinação, na ausência de luz. Então, é possível que esse efeito encontrado no doador livre não se repita no campo, em condições em que a degradação dele será mais acentuada, tá? Bom, em relação ao desempenho das plântulas, né, apresentamos aqui a comprimento e massa seca da parte aérea, comprimento e massa seca das raízes, tá? Na baixa temperatura, então, não tivemos efeito significativo, tá? Embora tenhamos aqui alguma superioridade numérica, e na raiz tivemos um aumento do comprimento das raízes com a nanopartícula carregada, e aqui também com algumas reduções nos demais tratamentos. Aqui uma figura da baixa temperatura, demonstrando maior quantidade de raízes laterais, raízes secundárias, e maior volume, Entretanto, estamos com alguma dificuldade para medir, para mensurar isso. Às vezes, na hora que fazemos a secagem e a pesagem, acaba não dando diferença estatística. Então, nós estamos ajustando as nossas metodologias para tentar avaliar isso melhor. A metodologia que a gente usa é uma metodologia adaptada para avaliação de lotes comerciais de sementes. Então, estamos com alguma dificuldade nisso. Em relação à temperatura normal, também o crescimento da planta, né, comprimento da parte aérea, aqui, ó, melhor desempenho da nanocápsula vazia, e aqui sem efeito estatístico. Comprimento das raízes, redução em algumas situações aqui da nanocápsula vazia, e aqui também reduzindo a massa seca, isso na temperatura normal. E na alta temperatura, podemos ver aqui um expressivo aumento do comprimento da parte aérea, nos 3 tratamentos contendo a nanocápsula carregada e até a nanocápsula vazia, tá? Isso não resultou em diferença estatística na massa seca, embora tenhamos aí uma considerável superioridade numérica. O comprimento de raízes também foi superior aqui em alguns tratamentos contendo a nanotecnologia e que não foi possível identificar na massa seca. Essa é uma figura do tratamento de alta temperatura, então vejam o quanto foi severo o estresse, levando as plantas praticamente aí à morte, né, as plantas ficaram praticamente cozidas, enquanto que o tratamento com nanotecnologia proporcionou maior tolerância a essa condição. Novamente, estamos ainda com algumas dificuldades para mensurar isso, tá? Avaliações futuras, penso que vamos conseguir. Diante desse resultado, fizemos uma quantificação do teor de doador, tá? Esse nitroso-tiol seriam os doadores de NO. E podemos constatar que nas doses contendo a nanotecnologia, o teor de doadores foi muito maior, né, a concentração foi maior em relação aos demais tratamentos, tá? Bom, quais são os próximos passos do nosso trabalho que ainda está em andamento? Então, estamos avaliando a parte bioquímica, tá? A atividade enzimática, o processo de peroxidação lipídica, produção de peróxido de hidrogênio, e todas essas partes bioquímicas, e também estamos conduzindo experimentos já em câmara de crescimento, para avaliar a performance fotossintética, e para avaliar o crescimento e desenvolvimento da planta, até um estágio um pouco mais avançado do que só aquele da germinação. Então, de maneira geral, os nossos resultados indicam que as respostas ao ácido giberélico são maiores no estresse por alta temperatura. Também as nanopartículas de quitosano e alginato vazias promoveram melhor germinação do milho sob estresse térmico por alta temperatura. O óxido nítrico também demonstrou maiores respostas no estresse por alta temperatura, de forma que tanto o doador livre quanto as nanopartículas aumentaram a germinação, porém com resultados mais interessantes no nano carregado. E o tratamento com o nano doador promoveu, então, maior concentração de doadores nas plântulas do que o tratamento que tinha o doador sem ser nanoencapsulado. Então, deixo aqui os meus agradecimentos à organização do evento, especial à professora Amedeia e ao professor Leonardo Fraceto, que são nossos parceiros que fornecem as nanopartículas, e a toda a equipe de nanotecnologia e agricultura na UEL. Obrigado. As perguntas podem ser feitas em inglês ou em espanhol, acho que dá para entender.
Thank you for your presentation, a very nice presentation and very interesting topic. We have some minutes for questions.
Okay, so we have a question here. Oi, André, diz Joana Peretti, perdão. Oi, André, parabéns pela apresentação. Você não compara as nanopartículas carreadas com ácido giberálico como as nanopartículas com óxido nítrico, certo? Você acha interessante uma aplicação combinada dessas duas nanopartículas diferentes?
Olá, Joana. Agradeço a pergunta. Então, na verdade, estou apresentando aqui resultados de 2 experimentos isolados, tá? Então, eu queria otimizar o tempo. Mas, se eu fosse trabalhar com os 2 juntos, eu teria um número de tratamentos muito grande, tá? Então, veja que eu já tenho o controle, mais 3 concentrações, 3 temperaturas e 3 tratamentos. Se eu colocasse isso mais 2 formas, combinação entre óxido nítrico e ácido giberélico, ficaria muito confuso, um número de tratamentos muito grande, e nós temos algumas limitações em termos operacionais, e sobretudo por conta dessas câmaras de crescimento, que elas não são tão grandes. Então, o nosso experimento já foi pensado para isso. Então, por isso que nós separamos. Então, conduzimos primeiro um, estamos conduzindo o outro. Acho que eu entendo que seria positivo combinar os dois, mas seria muito, muito difícil de entender o que está acontecendo se eu trabalhasse com os dois ao mesmo tempo. Tá? Então, acho que nesse momento a gente precisa separar para poder compreender quais são os efeitos y cómo esses efeitos acontecen.
Ok, muchas gracias, André. Tenemos otra pregunta, Wagner de Souza. Ótima apresentação, André. Parabéns. Quais as principais diferenças bioquímicas fisiológicas entre as respostas B? Entre as respostas...
As diferenças bioquímicas e fisiológicas, como eu falei, nós estamos no processo de avaliação ainda, tá? O experimento de ácido giberélico, nós não conseguimos ainda ver respostas fisiológicas, acho que talvez pelo momento de avaliação que não foi adequado. Então, essa é uma dificuldade. O ideal seria avaliar ao longo do tempo, e nós, a princípio, tínhamos optado por avaliar, esperar a planta se desenvolver e avaliar mais adiante. Então, penso que vamos ter mais respostas avaliando isso ao longo do tempo, após a germinação e emergência. As respostas bioquímicas, a gente ainda estamos fazendo as análises e não temos ainda os resultados para indicar. Nós conseguimos somente essa do nitroso tiol, que foi feito pela equipe da professora Medeia, que a gente conseguiu agilizar isso e processar os dados. E até optei também por tentar não trazer muito mais dados, porque eu estava apresentando 2 experimentos em 10 minutos, tá? Então, a gente ainda não tem muito claro quais são as respostas fisiológicas e bioquímicas por enquanto.
Ok, muchas gracias.
Só uma, Carla, se me permite um pouco.
Sim, por favor.
Sim, Wagner de Souza está aí, boa tarde já, André. Wagner, André, parabéns aí pela apresentação. E só para contextualizar esse trabalho, a gente está começando ainda. A gente sabe que o NO está envolvido em diferentes estresses abióticos, e estresse de temperatura é um deles. E com nanopartícula, né, André? Eu acho que não tem nada, né? Nanopartícula com doador de NO em semente, né? Em prime, em tratar a semente e fazer o estresse de temperatura. Eu acredito que não tenha nada. Então, a gente está tendo esses resultados bem interessantes. Então, a gente vai fazer um primeiro paper e, evidentemente, a gente vai ter que fazer uma batelada de estudos, de outros trabalhos, e seria um prazer aí envolver você, tá, Wagner? Depois a gente pode conversar junto com o Allen, né, que é o PI aí desse projeto, tá bom? Obrigada. Parabéns, André.
Obrigado.
Muchas gracias. Y una última pregunta de María Mercedes Martínez, que dice, could you please clarify if the nano nitric oxide was charged at lab, what was the source of chitosan?
Acho que essa pergunta a professora Medeia que vai saber responder melhor, porque ela que sintetiza a nanopartícula lá.
A nanopartícula tem carga, que é quitosana TPP, ela tem carga, ela tem uma carga positiva. O NO não tem carga, é um radical livre. E ele está perguntando sobre a carga, eu perdi. A carga? Carla, você está sem áudio.
Carla, não tienes áudio.
I'm sorry. Okay. Could you please clarify if the nitric oxide nano was charged at the lab, or what was the source of the chitosan? Si fue cargada en el laboratorio y cuál fue la fuente del quitosano.
Quitosana, a fonte é a quitosana comercial de baixa massa molecular da Sigma.
Ok.
E a primeira, eu ainda não entendi, desculpa.
Está perguntando se foi uma quitosana carregada. Acho que se refere na carga, né?
no laboratório.
Se for carga, se eu entendi correto, sim, ela tem carga e é positiva.
Acho que ela está perguntando se foi carregada no laboratório ou...
Ah, sim, loading, né? Desculpa, sim, fizemos o encapsulamento no laboratório e a gente tem uma alta eficiência de encapsulamento do doador de óxido nítrico. É mais de 90% carregado na nanopartícula. Desculpa, agora que eu entendi.
Não há problema. Muito obrigada. Creo que com essa resposta, não sei se está claro. Creo que sim.
Espero. Também, se não tiver, pode mandar perguntas. Depois a gente responde.
Tá bom.
Ok.
Thank you, dice ella, así que está.
Entonces, ¿podemos continuar con la siguiente charla?
¿Perdón?
Continuamos con la siguiente charla, entonces.
Sí, adelante. Gracias.
Ya, entonces continuamos con la charla presentada por el doctor Jorge Padrao de la Universidad de Minho, Portugal, quien nos presenta la charla titulada Biosynthesized fibrous-based meshes for abdominal hernia with enhanced mechanical and antimicrobial properties. Muchas gracias, doctor Padrao.
Hola, ¿qué tal? Muchas gracias por lo invito. Es un honor estar aquí con ustedes. En particular, lo quería agradecer a Gonzalo, a Dea y a Olga. Y es un placer poder compartir con ustedes nuestro trabajo, que voy con vuestro permiso, voy a presentar en inglés. Así, ¿está? So thank you once again. Thank you very much for the invitation. It was such an honor to share our work with you. It was a very friendly invite from friends. So it is really a pleasure to be here. It is a new project for our group. It's very recent and it has very few work done. We're just in the beginning, but we're very excited. So we would like to share our results with you on our approach, and maybe we could even share some insights if we're going in the right path or not, and if we can establish some collaboration or not. So let's just try to explain you a little bit what we're doing and try to teach you a bit of this field if you don't actually know much. So we're just going to show what we're doing. So we're trying to work with to solve a worldwide problem, which is the abdominal hernias. The abdominal hernia, by definition, is a protrusion of the peritoneal lined sac through the muscular neurotic covering of the abdomen. Which is very expensive words, but if we can break it down to a very simple thing, the peritoneal linnet, it's what's in pink here. So usually the problem occurs in the abdominal region. And basically when you have if it is compromised, the connective tissue, the muscle, there can be like a protrusion, something comes out. It's like an organ, it can be a blood vessel, it can be whatever, because if the muscle is not completely grafted, it will have a hole, and from that hole, an organ can stuck out. And that's basically it. You have a hole and something that shouldn't comes out. So what are the main risks involved to abdominal hernias to occur? Usually it's like when you have an abdominal surgery, it is quite obvious. So you're opening you're disrupting your muscle structure. So it's normal that structure will not have the same physical resistance. During pregnancy, if you have constipation, if you have an excessive weight gain very rapidly, when you're doing weightlifting due to the stress, the that you force your muscles to, or even by genetic factors. And there are several abdominal hernias. The most common ones are the incisional hernia, which is due to the, as we've spoken before, due to the surgery. You disrupt the structure of your muscles, of your connective tissue. And the second one is the umbilical hernia, and one of the most famous ones also, it's the inguinal hernia. So each abdominal hernia has its own symptoms. However, the abdominal hernia, all abdominal hernia have an ubiquitous symptom, which is the pain. So the patient always has some pain. It can be mild, you can still work, you can tolerate that pain, or it can be very serious and you can absolutely do anything. And there are two types of the abdominal hernias. Each one can have a mild discomfort or an excruciating pain, which are the reducible hernias and the non-reducible hernias. And the non-reducible hernias require urgent medical assistance, as I'm going to explain you the difference between them. So the reducible hernia, it is basically, as you can see, there's a hole in the abdominal wall, and here sticking out, it's the small intestine. It could be something else, but usually it is the most explained case study. It's when the small intestine comes out. So in the reducible hernia, it is possible to still have some transit of the nutrients that go across inside the small intestine. There is oxygenation of the cells that are here, so it's not a problem. They still are living. Of course, they're alive and kicking, but still it is a bit strangled. But the patient can live, and it's not a life-threatening situation. However, in non-reducible hernia, that's not the case. As you can see, there's a complete struggling of, in this case, the intestinal protrusion. So basically, the cells don't get any oxygen, they don't get any nutrients. So what will happen, it will be necrosis. So basically, the cells will start to die very rapidly, and that's a very huge problem. So the medical assistance has to be urgent. And is this common? Is this so common to have abdominal hernias? Yes, it is. Actually, there are estimated that 20 million hernias are surgically repaired, because at least in the United States, every 10 hernias, abdominal hernias, 9 of them are submitted to surgical repair. So you can have a reducible hernia, which is not life-threatening. However, sooner or later, your physician will tell you that maybe it would be better if you just repaired it. So you're going to go to undertake surgery. So it's absolutely normal. Unfortunately, this intervention is very common, and it has very low risk usually. And it has, in developed countries, it has a very, very low death rate of only 0.001%, fortunately. So what happened before 1958? Prior to 1958, the most common way to solve the protrusion of the organ of the abdominal hernia would be to surgically suture the region where you have the hole, and basically patch it up, and that's it. So you knit it, and that's it. It's done. But since 1958, that's not the most used strategy to solve this problem. Now we use usually a mesh. It's a hernia mesh. Like in the United States also, 9 of 10 hernia repairs, abdominal hernia repairs, use meshes. The type of mesh we'll see it's not completely unanimous, but the first and the most popular used mesh was the one used in the first time in 1958, which is a polypropylene mesh. So basically, instead of stitching, you just place a mesh, you fix it with stitches or glue even nowadays, and you just leave it there, and it will give higher support, higher physical resistance to your hole. So what happens is that it has its main advantages are the improvement of the post-operative comfort of the patient, and it reduces considerably the recurrence. What's the recurrence? The recurrence, it's when, if you have stitched, if you have the surgical sutured your hole, your abdominal hole, it will open again, and the organ will come out. You have another protrusion. So basically, you have to go back to the hospital and undergo surgery again. Of course, that's awful for the patient. It's bad for the health system. It is expensive. You have the post-operative stress, pain. So we should always avoid that. And the meshes considerably reduced the recurrence of the abdominal hernia. So this is the greatest advantage of using an hernia mesh, and it's kind of logical because you have something there, a net that will restrain your organs from coming out, or your blood vessels. So it's another wall. It's replacing your muscle and your connective tissue. So it works, and it works quite well. And but the hernia meshes have several requirements, not that simple. They have to withstand a tensile strength of at least 32 nanometers per centimeter. And this is when you sneeze. When you sneeze, you just press your belly so with a lot of strength usually, at least in my case. So it's normal that you have to have a mesh that can endure such a high stress. And the pores of the mesh have to be higher than 75 micrometers to allow the blood cells, fibroblasts, to pass through the pores and to establish the collagen, start producing collagen, allow the permeability and establishment of blood vessels and of fascia. So this is a mandatory requirement. And recently, it has been proven that when you have a pore size that's higher than 1 millimeter, the granuloma bridges between the individual meshes fibers, it's reduced. So you can reduce the stiff scar plates, or even reduce the probability of producing seromas and granulomas, which is when the macrophages group up and they start to attack a foreign in the body. So if you have a pore, larger pore, that has less probability of happening. So the hernia meshes have also 3 different classes, depending on which is the place that you're going to use type of mesh. They have 3 different weights. And what kind of materials are used nowadays to produce hernia meshes? So basically they're from petrochemical-based meshes, which you have the famous polypropylene, which was the first application, the first mesh ever used, the polyester, polyestyrene, you have PTFE, and of course, nowadays you have the biological meshes, which are composed of a cellular tissue from human origin, from animal. Usually when it's animal, it's from cattle or porcine. And they're basically, what is a cellular tissue? It's very easy to explain, because you have in this case, we have an adipocyte, like fat tissue, which is covered with adipocytes, which is this one here. And when you process this type of tissue, and you remove all your cells, so it's called a cellular, it has absolutely no cells, it will still maintain its collagen structure. Usually in fat, it's collagen 4, which is the most prevalent collagen. So basically, you maintain that structure. And this structure can be used as an hernia mesh. It can be used as an area mesh, and this a clear example that it has a big difference between when you have an intact tissue and a cellular tissue. When you remove the cells, obviously you also remove the genetic information. So it is quite obvious that in this graphic here, the DNA content of the samples, it is completely different. It's statistically robust, the difference. So basically, and this is key to avoid any further foreign body reactions, so rejection from your grafts. So within the petrochemical-based meshes, which are the most common ones, they have several key advantages, which are the low cost. They're adequate for simple interventions, which are the most common also. They are usually adequate only when you have no infection in the wound, and they are for simple bridging, they will work. And of course, they have a higher shelf life than the cellular tissue. The disadvantages, the main disadvantages, is that they cannot be used in infected areas. And when they are inside, they're implanted in your body, they usually degrade over time. And this degradation can lead to reoccurrence because they're not absorbable materials, they are not degradable. So they're supposed to stay in your body until forever. So they're not supposed to degrade. So it is a problem they have. It's a big disadvantage. Actually, in my opinion, it's the main disadvantage, one of the main disadvantages. So in terms of biological-based meshes, you have the most important advantage is that they can be used in infected areas. Because usually when you have a non-biological mesh, the bacteria in the infection, they will love the surface of the petrochemical-based meshes, and they will start adhering and producing biofilms, which are very, very hard to deal with. So that's the main advantage of biological-based meshes. The main disadvantage, obviously, one of them, it is very expensive. It's obvious, everyone can see that this process of taking out the cells, it won't be cheap. And the hernia meshes are an important market. They reached in 2016 $177 million, and there are plenty of them. Different manufacturers, different graftings, different properties. Nevertheless, the ideal hernia mesh, and this is something that all physicians, doctors in the world agree on, is that the ideal hernia mesh was not yet developed. And the most commonly used still, it's the same polypropylene mesh that it was used almost 60 years ago. So there is a big discovery hole here that we want to contribute to. But there's a big problem here because there's the petro versus bio, as I usually say. And this is no easy task. Everyone knows that petrochemical-based compounds are good, they're sturdy, they're reliable, easily produced, you can produce it in every shape, size, can extrude it very simply, and they're very, very reliable. However, everyone knows the environmental problems that they represent, and we want to, at least me personally also, want to start to have a more biologically approach to use the best properties of biomolecules to replace the petrochemical molecules. And this is no easy task. But I think we can do it if we do bio-based nanomaterials. So that's my opinion, and that's our approach for this project. So we're going to use a fully bio-based material, which is produced by bacteria. So this is a bacterial nanocellulose bacterial producing cell, and it's through its normal metabolism, it naturally produces extruded cellulose. So it will extrude nanofibers of cellulose, which will build up and produce a three-dimensional mesh of nanofibers of cellulose. So it's called bacterial nanocellulose. And you can see it here, it grows within the shape of the vessel that you grow. When you grow it in static culture, it will produce a film on the surface of your flask, and when you remove it, of course, it has this yellowish color, which is usually associated to the color of the culture medium. However, with a simple purification process, you can obtain pure nanocellulose, which has this more friendly white look. And it has several outstanding properties. One of them is that it is composed solely of cellulose. Its nanofibrils have a diameter of 20 to 100 nanometers. So we're surely talking about a nano material. It has the 3D hydrogel nanomesh, which means that most of it is water. It's non-absorbable, which is great if you have a permanent implant. Everyone knows we're not able to degrade cellulose naturally. So it also allows, due to its high water content, it allows effective gas and nutrient diffusion, and the surface shape is defined by the culture vessel. So if you have a squared vessel and you're doing your culture there, it will be squared. If it was bound circular, you would get a circle film. If you have a star-like vessel, you would get a star-shaped bacterial nanocellulose film. So it is very easy to control its shape. It's macroscopic shape. The endotoxin level after the purification, and since usually the bacterial nanocellulose is produced by gram-negative bacteria, it was expected that we have a high level of endotoxins, but no, the level of endotoxin is just 1 EU per liter. The FDA has a threshold of 60 EU liter for some compound that will get in contact with cerebral spinal fluid. So it is very, very far away from the limits of the FDA, the Food and Drug Administration of the United States. And in terms of physical properties, physical mechanical properties, I always love to show this table, which clearly shows that the potential of this material. As you can see, of course, wood doesn't have a very high Young modulus, but cotton, just like bacterial nanocellulose, it is fully composed of cellulose. So it's 100% cellulose as well. And you can see the difference is striking. And the density is not that different. The crystallinity is not that different. The degree of polymerization, it's not that striking as well. But as you can see, bacterial nanocellulose, it's much more closer to the mechanical properties of Kevlar. So no problem. When we go to the RNA meshes requirements, we can stamp a big check mark on if it is able to withstand the sneezing of a person. Of course it can. So let's go, do we have the pores? And let's check if the bacterial nanocellulose has the following requirements or not. So let's check if it has the pores right. No, it doesn't. The pores are very small, very, very small due to the nylon fibers. So it has only 20 to 300 nanometers in size. So how are we going to solve this? We're going to do, using a 3D printer, we're going to build a mesh template, which will have the rods protruding the culture medium, and these rods will have the size of the pores that we want. Then we'll immerse this template in the culture medium, in static culture medium, and we'll allow it to incubate. And the bacterial nanocellulose will form within these holes, within these rods. So in the end of the culture, you just have to remove this bacterial nanocellulose, and you'll have the holes of the rods. So you'll have the pores with the pore size that you want. And since it is very sturdy, the bacterial nanocellulose, you can actually remove it without many problems. So that's another big check mark for this requirement. Now, in terms of granuloma formation, seromas, and stiff scar plates, how is it going to be? So when you do perform the hernia mesh, when you use an hernia mesh to solve your abdominal hernia, the first thing that will occur immediately after you do the chirurgical procedure will be the collagen type 3 will quickly envelop the mesh. It will happen in whatever healing process that will occur. If you have a scar, it will be the same. And this collagen type 3 should be promptly replaced by a more mature and more sturdier collagen, which is the type 1. However, this transition can, and usually it is, unfortunately, delayed when the body finds that, hello, this mesh is not mine. This is a foreign thing. So this is delayed, and it will cause several problems. One of them, it will lower the mechanical stability, because collagen type 1 has higher mechanical stability. It will cause the shrinkage of your mesh, and it can also lead to the stiff scar formation, which is awful. Usually it has pain associated, and it also can have problem in terms of mechanical properties, because it will be stiff, it won't be flexible. It will hinder your mechanical stability. But bacterial nanocellulose does not induce foreign body reaction. This is stated in several studies, and one of the reasons that it is proposed for this not to happen, and this is a proposition, it's not yet confirmed, is that it is its structure, its architecture, it's very similar to that of collagen. So you have the collagen here on the left, and you have bacterial nanocellulose on the right. They're a bit different in terms of scale, but when you reduce the bacterial nanocellulose, it will look a little bit like the collagen. So one of the reasons may be that the cells get to the location when you have the bacterial nanocellulose, and they do not only face a natural product, but they also think this architecture is very familiar, so they're not going to react against it. So a big check mark for this one as well. We won't have any seromas or granulomas, hopefully. So what about the hernia mesh classes? Can we follow this requirement as well? And I can already tell you that yes, because we worked a lot with this bacteria. We're now working with it. And this bacteria that produces bacterial nanocellulose can reach a density of nearly 800 kilograms per cubic meter, which means that the bacterial nanocellulose, due to its nano size, you can easily control the density, and it has an outstanding density that normal materials cannot achieve. And you can control the quantity of bacterial nanocellulose by just controlling the type of bacteria that you're working with, the culture medium that you're working with, or even the incubation time. If you allow bacteria to grow with a little bit of time only, you'll have a very thin, not very dense bacterial nanocellulose. But if you leave it for a long time, from about 1 month, you'll get a big chunk of bacterial nanocellulose. So a big check mark for this one as well. So we're on the right path, I think. But there's another problem that was not specified earlier, which is the hernia mesh infection. Yes, it's true that it happens only in less than 4% of the cases, but if you observed the lecture of Professor Andrea Zille, you knew that he was highlighting that we're trying to find a way for our implants or our meshes to have antibacterial activity, antimicrobial activity for about 8 months. And the reason is this one. It's because you have the first signs of infection in hernia meshes do not occur immediately after operation. Actually, they don't happen weeks after the operation. They happen months, actually almost years after the operation. So and they're extremely tricky they're very, very complex. They're very hard to solve. So basically the only solution, the only viable solution is to remove the mesh. So you have to go to surgery again with all the associated problems with that has. So basically we are producing using 2 different approaches to embed nanoparticles that have antimicrobial activity within our bacterial nanocellulose, so they have these antimicrobial properties. So one of them is by producing in situ. So we have the nanodots that will be embedded in the solution with the bacterial nanocellulose, and then we'll promote the synthesis, the growth of this nanodots to nanoparticles in nanoparticle size, and so they can be entrapped inside our hernia mesh, our bacterial nanocellulose hernia mesh, so they are not released and they don't go to the bloodstream, which is essential for this to work. Because usually when you have nanoparticles that are lower than 30 nanometers, they can easily pass the blood-brain barrier. So that's a big no-go. And then we have another approach, which is a more simpler approach that we're using now, which is the adsorption through filtration. So we have a solution of nanoparticles and we force their filtration through bacterial nanocellulose mesh, and they are within that entrapped within the bacterial nanocellulose nanofibers, and hopefully they won't be released, but we are going to confirm that. So when we have the ideal formulation of the bacterial nanocellulose and nanoparticles, already with the right pore size, we're going to try and check through antimicrobial tests if it has the ability to kill bacteria, the ability to kill fungi, and also we are now able to confirm if the bacterial cellulose with nanoparticles is able to kill bacteriophages. Viruses also, which is the trend way. We are using actually now the MS2 bacteriophage, which is very similar to the SARS-CoV-2 virus. It has the same architecture. It has also has RNA as its genome, but it only affects bacteria, so it's safer to work. And we're going to do the cytotoxicity tests also to see if there's some cytotoxicity associated with these nanoparticles, because usually bacterial nanocellulose, usually no, always, fortunately, doesn't exhibit any cytotoxicity. So in the end, we just have to do the optimizations, establish the different weights of bacterial nanocellulose meshes, and we're hopefully can achieve a patent in the production methodology and even have a commercial product. We shall see, but that's the final step. So thank you very much. I would like to acknowledge my supervisor, Professor Andrea Zil, Liliana Melru, which is the PhD student more involved in this project, also Anna, and we are also with the consultancy of Dr. Fernando Ferreira, which is actively working with hernia meshes, and he was the one that alerted us that there is no ideal hernia mesh still. So this is a problem that you have to solve. And Professor Miguel Gama and Fernando Dourado, which are the experts also in bacterial nanocellulose, actually they taught me everything about bacterial nanocellulose. And also would like to acknowledge the funding and do a little bit of marketing, that we have 2 special issues here. If you are interested in submitting your work, please just contact us. And that's it. So thank you very much. Muchas gracias.
Well, thank you very much for your presentation. It was very good, and it was an excellent presentation. Now we have time for a couple of questions, I guess. So you are all welcome to write your questions or ask them directly from here. So, is there any question? ¿Alguna pregunta? ¿Están abiertos los canales?
Yo posso fazer uma pergunta.
Adelante.
Charles, very nice presentation. And it's interesting how the nanocellulose is using right now. We used to work with the nanocellulose from wood, okay, not from bacteria. But it's looked like bacteria, it's looked quite nice system, okay? So I'd like to know the prices. How many is cost related to the another cellulose?
Well, hello, Professor Duran. Thank you very much for your question. I was missing you. So it's thank you for the question. It is the problem here. It is the type of nanocellulose, because when you have carbon nano needles of cellulose, the carbon the nanocellulose, the needles, the whiskers of cellulose, those are the cheapest ones. They're much cheaper than bacterial nanocellulose. Good. But bacterial nanocellulose is not that cheaper than the nanofibril cellulose. When you have a mechanical process, which is usually always is very energy intensive, so it's not viable. So in terms of prices, but there's an advantage in bacterial nanocellulose instead of nanocellulose crystals. Right. The nanocellulose crystals, they have very, very, very low density. So you have liters and you only have a very few nano needles of cellulose. True. The bacterial nanocellulose has high density. It's very easily, you can get high density, and it's cheaper than the nanofiber cellulose, which is obtained by the mechanical treatment. However, it's still expensive, because if you use a rich culture medium, it's expensive. However, there are very many research groups that use byproducts from the industry, from sugarcane, they use corn steep liquor, and they can reduce the cost of bacterial nanocellulose. banana peels, they use a lot of different media, and that reduces a lot the cost.
Yeah.
So it's not that expensive in terms of the rest of the
yeah, I agree. Thank you, George.
No problem. Thank you.
Good to see you.
Good to see you too.
Thank you very much. So we have a question from Nicolas Hoffman. And first he says, thanks for the presentation. And his question is, what's the maximum production yield of nanocellulose that you can achieve?
Oh, the maximum. That's a very hard question to say it. I don't know by heart the yield. But it is, I don't know. I'm sorry. I have to check. I don't want to say that, but please contact me and I'll answer. I just don't want to say something that's not right.
Okay, we'll send you.
You got me on that one.
Okay, thank you very much. And Isabella Martins says, great job, Jorge. Congrats. Interesting approach to this topic with meshes and nanoparticles.
Thank you.
Congratulations. Well, thank you. I think there are no more questions, so we can move on. Thank you very much.
Obrigado. Gracias.
Paola, ¿estás silenciada? Sorry. A continuación vamos a presentar al doctor Ale Caixeta, perteneciente a la Universidad Estadual de Londrina, Brasil, quien nos presentará el tema Application of Nitric Oxide Releasing Nanoparticles for the Protection of Plants Against Biotic Stresses. Thank you.
Okay, thank you for the presentation and for the opportunity of sharing our results with you. So just a minute to, let me just put one, okay. Are you hearing me and seeing the presentation? Okay.
Yes.
Yes, no problem.
Okay. So my name is Ale Caixeta de Oliveira from the State University of Londrina, and I will share with you some of our results about the applications of nitric oxide release nanoparticles for the protection of plants against abiotic stresses. So many types of polymeric nanoparticles have been developed as carrier systems for active ingredients with agricultural applications, such as we have, let me just change here, as herbicides, insecticides, fungicides, and also plant growth regulators or biostimulants. And the nanoencapsulation of the active ingredients into the polymeric nanoparticles can have several advantages, like the controlled release, the protection against degradation, increased solubility, improved efficacy, and also the decreased toxicity to non-target organisms. And my research group has been collaborating with many other groups, evaluating the effects of these nanosystems in plants. For example, we've been working with Dr. Fraceto with the atrazine loaded PCl and azein nanoparticles. Dr. Fraceto told you something about that yesterday. Also, the nanoparticles containing botanical insecticides, we also have worked with them. Also with Professor Dr. Medea Seabra and Renata de Lima, we worked with some biogenic metallic nanoparticles and copper and chitosan nanoparticles containing copper ions, also with aiming at both as nanofertilizers and also as for fungi control. And we also work with nanoparticles loaded with plant growth regulators, more specifically gibberellic acid and nitric oxide donors. In my talk today, I will focus only in this part of my work. So I will begin it with talking about a recent opinion paper that has been published this year in Journal of Agriculture and Food Chemistry by a Spanish group, in that they say that the title is Biostimulant Nanoencapsulation, a new keystone to fight hunger. And in this opinion paper, the authors, they propose that they show that the promising use of the nanoencapsulation of biostimulants for increasing the yield and the plant test tolerance in an eco-friendly way. For example, this images from this article, and they show that if you nanoencapsulate a biostimulant, like a plant hormone, for example, it can allow a controlled release of this biostimulant, and it can protect it from the degradation. This is a very important point, because the biostimulants, the plant hormones, they are very prone to the degradation in the soil, also by light. They are very sensitive. So the nanoencapsulation would protect them from degradation and allow a controlled release. So you can maintain a good amount of these compounds, of these active ingredients in the soil, and then it can result in an enhanced plant defense and enhanced growth, and also a higher production. So in these ones, in this opinion paper, they say that in spite of these promising applications, there are so few studies with the development of nanoencapsulated biostimulants. They cite only 3 studies published up to now, like this, the nitroxide release chitosan nanoparticles, the GA3 loaded chitosan nanoparticles, and the salicylic acid loaded chitosan nanoparticles. All of them are made of chitosan, which is a biodegradable, a biocompatible polymer. So it's very important to have an eco-friendly product. And all these, the nitroxide, GA3, the salicylic acid, are natural products that are present in that do not bioaccumulate, so that it would be an eco-friendly strategy. And from these 3 studies that they cite, 2 of them I am involved in 2 of them, with the nitroxide release chitosan nanoparticles and the GA3 loaded chitosan nanoparticles, and I will talk a little more about them today for you. I will focus mainly on the nitroxide release chitosan nanoparticles, but then I will also talk a little about the GA3 loaded nanoparticles. So talking about the nitroxide, the NO, it is an important gaseous signaling molecule in plants. It plays many roles in plant development and growth, since from germination to senescence, and also it has a very important role in the induction of plant resistance, in plant tolerance to stresses, both biotic and abiotic stresses. And so, and many studies show that the use of nitroxide donor molecules, so molecules that that release NO to increase the plant tolerance to stress. But there are many studies, academic studies about that, but the application of NO donors in the agriculture is still scarce. And it can be related to the relatively fast degradation of these compounds under uncontrolled conditions, under field conditions. Because here we have the example of S-nitroso MSA, that it is a S-nitroso thiol. We have here the thiol group, the S-nitroso group, and this molecule it decomposes to release NO. But in the presence of the light, high temperature, in the presence of metallic ions, it can release the NO so fast. So we have a high amount of NO in a short time, and it can be toxic to the plant. So, and it loses the signaling function. So this is a problem that can hinder the application of these NO donor molecules in the agriculture. But there has been a successful application of NO release nanocapsules in the biomedicine. So there are in health, in medicine, there are many studies that use the nanoencapsulated NO donors to release the NO. And Professor Amedea and Dr. Seabra, she had many works about that. And they made this question with her co-authors in this review, if these NO-release nanocapsules could also be applied to plants. So it could be also try this to apply these NO-release nanocapsules to increase plant tolerance to stresses. And we begin this collaboration because during my formation, I worked, my PhD was with NO, so I had a lot of interest in studying NO in plants. And we begin this collaboration to evaluate the application of these nanosystems in plants. And indeed, we can show this result here. We have here the NO release profile. Here we have the NO levels, the time. We observe that the free S-nitroso MSA, the free NO donor, it releases the NO very fast. So we have high amounts in a short period of time. While the encapsulated NO donor, it releases NO much slower, but in a sustained way. So you can keep low amounts of NO for a longer period. So it extended, the nanoencapsulation is extended the half-life of the NO donor and allowed a slower release of the NO for a longer period. Then we try this in plants. We apply this to a plant model. We use as a model maize plants under salt stress. The maize plants were grown in a substrate with a high amount of salt. And first, we observed the S-nitrosophiles content in the plants, in the leaves. And we could observe that the treatment with the nanoencapsulated NO donor resulted in a higher amount of S-nitrosophiles in the leaves, higher than the free S-nitroso MSA. So the nanoencapsulation improved the bioavailability of the NO to the plants. And then we evaluated the biological effect, the stress protection. And we could observe that here, evaluate the photosynthetic activity. We evaluate the photosystem 2 activity. You can observe that the salt stress leads to an inhibition of photosystem 2 activity, as well as a decrease of chlorophyll content. But when we treated with the free S-nitroso MSA, at 50 micromolar, it does not have an effect. But if we treat with the nanoencapsulated NO donor, you can see that it protected the plants from the inhibition of photosystem 2 and from the decay of chlorophyll content. So the nanoencapsulation improved the biological activity of NO and protect these plants against abiotic stresses, against salt stress. And we can see this in these images. You can see here the control plants without salt. In the presence of salt, you can see their aspect, their chlorosis, necrosis. But if you treat with salt and the free S-nitroso MSA, we can see just a partial recovery. But if we treat with the nanoencapsulated NO donor, you can see a big difference. So a better protection against these abiotic stresses. So, and this study was the first report on the application of nanoencapsulated NO donor in plants. And it also had, it was the study of my undergraduate student, Bruna, and also of Milena, who was the Amedea's student. We used other models to test these nanoparticles. We used soybean plants cultivated in soil with copper excess, which is a very important abiotic stress, as the application of copper-based fungicides can lead to the accumulation of copper in the soil. And you can see here that the application, that the excess of copper in the soil here is 300 ppm. You can see that there is an inhibition of root growth, mainly the growth of their roots is hampered by the excess copper. If we applied the free NO donor, there is almost no difference. But if we treat with the soil, if we apply to the soil the nano-encapsulated and no-donor, you can see a big difference. You can see a improved growth even in the presence of copper. So the nano-encapsulated and no-donor prevented the copper-induced inhibition of root growth. And it also, it was related to a protection against oxidative stress. You can see here that the copper excess increased the levels of hydrogen peroxide and also the lipid peroxidation in the roots. But if we treat the plants with the nano-encapsulated and no-donor, you can see that the oxidative stress is decreased. The hydrogen peroxide levels are decreased to the levels of the control without copper, and also the lipid peroxidation is also decreased. This was the work of my master student at that time, of the Diego Gomes, who was in the master during this time. We also use neotropical tree seedlings to apply the nitric oxide releasing nanoparticles, aiming at obtaining seedlings more tolerant to stresses. Think of the restoration, about forest restoration. Here we have a study with Heliocarpus papayanensis. We have here the image of them in the nursery, and we also treated them to the substrate with the NO release nanoparticles and releasing nanoparticles. And we also observed that the nano-encapsulated and no-donor promote the growth of these seedlings growing under high light stress. You can see here increase of leaf area, stem diameter, dry wave. So there was a positive effect of these nanoformulations in the acclimation of these plants, in the growth of these plants under high light stress. This was the study of Patricia, a master student. And we continue to work with the Heliocarpus papayanensis with neotropical tree seedlings. Now we are working with them in drought stress, in water deficit, which is another very important abiotic stress in restoration areas. And we also observe a positive effect of NO releasing chitosan nanoparticles in the protection against drought. You can see here that the treatment with the nano-encapsulated and no-donor increased the hood hair incidence. So there was a higher amount of hairs in the hoods, absorbent hairs. So it could improve the water uptake by the plants, by the stressed plants, and then it resulted in a higher relative water content in the leaves. You can see here that here is the field capacity, the control, the well hydrated plants, more or less 90% of water in the leaves. In the water deficit, there is a decrease of this water content, but even the plants in the water deficit, but with the previously treated with the non-encapsulated and no-donor, you can see that the relative water content is the same as of the well-hydrated plants. So the production, the formation of hood hairs improve the water uptake and allow these plants to keep the water content even though they were in a dry soil. And it allowed an increase of to maintain the stomata open, so it kept the stomata open, and then they could make the photosynthesis and assimilate the CO2. So, and this effect was more evident when we used the nano-encapsulated no-donor. With the free no-donor, we can see just the effect on the stomatoconductus and on the photosynthesis. If we used the nanoparticles without NO, we observed no effect. So the effect was related to the NO. And this manuscript has been submitted recently. It was the work of my undergraduate student Giovanna. Now we are aiming at understand better the interaction of these nanoparticles with plants and also their mode of action. we intend to do something that was similar to which has been done with the nanoatrazine, which Leonardo Frassetto, Dr. Frassetto showed yesterday. We will try to use the fluorescently labeled nanoparticles, so you can track these nanoparticles in the plant tissues, and also you can also measure the NO production, use the fluorescent probe, so you can see if you have a co-localization between the nanoparticle and the NO or not. So we want to understand better this interaction, if the plants uptake or not the nanoparticles, if only the NO enters or only the NO donor. So we want to invest now in these aspects. I'm going also to show briefly some results with the GA3 loaded chitosan nanoparticles. And these studies were in collaboration. This system has been developed by Dr. Frassetto, also the PhD student at this time, Anderson Pereira, and they observed an increased germination of seed germination of common bean plants when they were treated with the GA3 loaded chitosan nanoparticles there. So there was a positive effect in germination and also on plant growth, increase of leaf area. So the GA3 loaded chitosan nanoparticles allowed a better germination and initial growth of these plants. But common bean plants, they have a high germination rate, and we are now trying to observe the effects of these nanoparticles in seeds with physiological dormancy. For example, some bromeliaceae, which are like Dicea aurea. It's a neotropical plant here, a native from Brazil, and it has a physiological dormancy. And we observe that the treatment with the GA3 loaded nanoparticles increase the germination speed index, and also increase the dry mass of the plantlets. You can see here the difference between the treated ones and untreated ones, and it could have a very important effect on the very important applications to the micropropagation of these plants, of these endangered plants, and also for the species conservation. So these species have very important ecological roles, as well as it can have ornamental applications. And this work is the PhD thesis of Jean, together with Ricardo Faria from WELL. And also something, finally, Anderson, during his postdoc with Dr. Frassetto, he also observed a very interesting result with these GA3 nanoparticles with seed priming. He treated the tomato seeds with these nanoparticles and observed not only an effect on germination and on initial growth, but also an increased fruit productivity in plants grown in realistic conditions. We can see here the fruit productivity. You can see here that the treatment with the chitosan TPP or alginate chitosan nanoparticles contained in the GA3, you have a higher productivity of fruits than the other controls, the free GA3, the non-nano GA3 with the nanoparticles without GA3. So and it was interesting because the treatment has been done in the seeds, and this seed priming has a long-term effect on plants. So we are now trying to understand the mechanism of action, how these effects occur, also the effects on soil microbiota, and also the use of these nanoparticles in the protection against abiotic stress, as André has shown for you today earlier. So I'd like to say thank you, to acknowledge all the team of the Laboratory of Plant Ecophysiology of WELL, as other collaborators from the State University of Londrina, the post-graduation programs, as well as all the collaborators, especially Dr. Amedrea Seabra, and also Dr. Leonardo Frassetto, who developed these two nano formulations, which I showed for you today, also the funding agencies and the organization of the workshop for the opportunity, especially Gonzalo for the invitation. So thank you. Here you have my email. If you want to contact me, you have my email here.
Thank you very much for the interesting presentation. I have some minutes for questions.
Okay, so we have a question here from Wagner de Souza. Hi, Hailey. Great presentation. 2 questions. The first, are you using or planning to use omics to study the basic mechanism of the protective effects of the nitric oxide in plants?
It would be great. It would be great. For a while, we are not trying this, but it would be really interesting. Both metabolomics, genomics, some genomic assays could indeed give important information about this mechanism of action. I think we are going to try only some microbiome. We are going to try some soil microbiome to analyze the effects of these nano formulations on the soil and the plant microbiota. But I agree that the evaluation of the genomics, transcriptomics, and metabolomics data could give very important information also.
Okay, thank you. And the second question, do you have an idea which type of nanoparticle could be used to deliver genetic material or proteins in plants?
Oh, I'm not sure about that. Perhaps Medea could answer better this because I know that there are many studies that show that the development of nanoparticles that can deliver genetic material, but I don't know exactly which are the materials that are used to produce these nanoparticles.
Yeah. Okay, thank you very much.
Just Carla, just 1 second, and thank you, Wagner. So I think that after this conference, we might talk together, Ali and Wagner, because we can work together with the proteomics, metabolomics. So we have a lot to do. And regarding the kind of nanoparticles, this is something, Ali, that with Wagner, we are going to start working with gene delivery. I think that chitosan nanoparticle might be a good candidate, I suppose, so I'm not sure. But we need to think about this kind of nanoparticle. But I suppose that chitosan or alginate could be suitable.
Yeah. And as you talk about the proteome, something that would be really interesting is to evaluate the S-nitrosoproteome. Probably it would be great if you could see that, to see which proteins are nitrosated by NO, depending on the nanoencapsulation. It would be really interesting to do that.
Yeah, because we quantify the total amount of S-nitrosothionein, but we don't know what proteins are modified by the nitric oxide donor. So this might be a huge step, future work for us to do. We are very interested in this topic, for sure.
We have another question here from Camila. Ella dice, los donadores de,
Can be in Spanish.
Ok, los donadores no podrían aumentar o disminuir el estado de dormencia de las semillas. Eso sería bueno para el almacenamiento de los cultivos comerciales.
In the case of the bromelias, we can saw that they have this dormancy, and with the treatment with the no-dormans break this dormancy. So you can use it to break the dormancy and improve the germination, but not for storage. For storage, it's not good. So for the storage, it's better to keep the dormancy. So you can treat with the no-dormans when you want them to germinate, as the example I gave in the case of the bromeliaceae. So it depends on the timing when you apply this nanodonor. I don't know if this treatment can induce a long-term effect and affect the dormance of the generation of the next generation. I don't know. Perhaps can have something about that. If you treat the seed with the nanodonor, it breaks the dormancy, that germinates, then it produces new seeds. This seed, I don't know if you would have effect in this seed, the next generation. I don't know, but it's something to check.
Okay, thank you very much. Is there other question?
I have one question. What quantity of nanoparticles do you apply in experiment performed under greenhouse conditions?
In the greenhouse conditions?
Sí.
Yes, I treated in the greenhouse conditions, with the nitroxide releasing nanoparticles. All studies were we had studies in the greenhouse, but we did a study in the nursery also. With the GA3 release nanoparticles, there were some studies in the in vitro studies, and also the study with tomato was in real conditions in a greenhouse that it was really used for a farmer to produce tomatoes. It was a realistic condition. So, but with the nitroxide, now it would be very important to test this nitroxide releasing nanoparticles in field conditions. It's something that we need to do soon to evaluate then the effect on the productivity in a real condition. But we tried only in the greenhouse, and we tried it then in the nursery in the case of the seedlings, the 3 seedlings.
Okay, thank you.
Thank you.
Okay, so we don't have any more questions, I think. No.
Ok, entonces agradecemos nuevamente al doctor Heile y continuamos con la siguiente charla. ¿Sí?
Yes.
Bueno, la siguiente charla la presentará Dayana Silva Ávila de la Universidad Federal dos Pampas, Brasil, y se titula Nanomaterials and Gynoherpetitis Elegans, Advances and Challenges Using this Model in Nanotechnology. Gracias, Dayana.
Hello, how are you guys? I hope everyone is fine as well. Are you hearing me well? Can you see my screen?
Yes.
Yeah?
Yes.
Okay, great. So I would like to thank the organizers for the opportunity to share our studies here. I'm gonna show you different types of studies because my idea is to open our lab for collaborations. Okay, so it's a great pleasure to be here, and congratulations for this great workshop. I've been learning a lot during these 2 days. Excellent talks. So I'm gonna talk first about Xenohabiditis elegans, which is the animal model that we use to assess the toxicological aspects of different types of nanomaterials. So C. elegans is a small non-parasitic nematode. So as you can see here, is a transparent worm, but it's important that it's not parasitic. It lives in the organic matter. It lives in the wherever there is organic material, C. elegans is there. So this is quite interesting for the studies that I will share. These worms, they have short life and reproductive cycles, so we can get results very fast in a short amount of time. In addition, these worms, they can give you large progeny, so the reproduction system, the reproductive system is quite interesting to evaluate because it's very sensitive. These worms, basically, they eat and they reproduce. So it's quite a good endpoint to analyze. Mostly important for some studies, especially when we assess nanomaterials focused for nanomedicine. These ones, they have high homology to the human genome. So around 60 to 80% of the C. elegans genome is quite similar to the human genome. So this is very interesting to translate the findings from worms to humans. Also, it's very easy to cause a genetic manipulation in these worms, so to generate transgenics, to generate mutants, and to do RNA interference. So, for example, we can get interesting strains that express a green fluorescent protein in specific protein, target proteins. So, for example, we can label some neurons, and we can label even especially neurons, and analyze their fluorescence, and analyze, for example, if some nanomaterial is being neurotoxic. So we can see if the neurons are decreasing the fluorescence. Maybe it's because they are dying. Okay, so this is just one example. And this is fantastic because we can see all that in vivo. Okay, so as you can see here, the animal is moving, so we can analyze all that in vivo. Okay, we can analyze any kind of protein since someone has created or generated with transgenics. I think some microphone is open. I can hear some sound, some feedback. I'm sorry. So C. elegans is quite interesting to analyze different types of nanomaterials, those used for biomedicine, for example, and those that can be used for agricultural purposes. So C. elegans is a great platform because it combines in vitro, like in vitro assays, but also considering that the organism is in vivo animal and has many organs and tissues that are very similar to mammals. So basically, C. elegans is in between in vitro and also in vivo models. And also nematodes, they are invertebrates. So this is, it helps us to do nanotoxicology because we don't need to be concerned about bioethics issues. So we can use as many worms that we need to do all these studies, okay? And also another important factor that I mentioned is that these worms, they live in the organic matter. So wherever there is an animal or a fruit that's rooting, these worms, they are there helping to degrade. And then they live in the soil. They are part of that environment, okay? So nanomaterials, we know they are everywhere now. They came from, we are exposed to nanomaterials from different sources. We just saw a talk earlier by Professor Luis talking about an assessment in a company. And this is, it's very interesting. We are being exposed to that by the environment or by occupational, our occupational activities. So we are exposed to different types of nanomaterials, different sizes, materials, shapes, and etc. But we need to know, we need to be sure how safe these nanomaterials are for health and also for the environment, of course. So my lab has been receiving different types of nanomaterials from different sources. So here you can see all the universities that are collaborating. And as I told you, my lab is open for new collaborations. We would be happy to do a safety assessment of the nanomaterials you are working with, okay? So for example, I'll give you just some examples so you can see how can we apply the nematode C. elegans for nanotoxicology. So for example, we assessed a nanomaterial, a nanocapsule that was used, combined curcumin and quinine. Both drugs have been used for malaria treatment, but they are quite toxic. So we associated these two drugs in a nanocapsule, in a polymeric nanocapsule. The polymer used was polyepsilon caprolactone, and we observed that the nanoencapsulation protected from UVA degradation, okay, because these molecules, they can be easily degraded. There was an increased efficacy of these two drugs combined in the nanocapsule against Plasmodium falciparum. So the efficacy was higher than when those two drugs were combined, but not in a nanocapsule. And also, we observed a decreased toxicity of these two drugs when they were administered in nanocapsules versus their combination without the nanocapsulation. So this is amazing, right? And something else that we could verify is that when we functionalize it, we didn't need actually to functionalize these nanoparticles because curcumin and quinine, they are both autofluorescent. So we basically could give them to the worms, these nanocapsules, and we could see that the worms ingested these nanocapsules, right? You can see around the body of the worms, and we could see these fluorescence even after 24 hours exposure. So these worms, they digested the nanocapsules and they were distributed. So this is something very interesting because many people ask, are they ingesting, are they absorbing the content of the nanoparticles? And we believe so because of this data. We have been also working with some inorganic nanoparticles of interesting in biomedicine. Professor Amedea, she sent us some nanoparticles. They are of magnetite, decorated with silver, and they were synthesized by biogenic growth using green tea. And we analyzed the safety of these nanoparticles. Yesterday, Joanna presented some very interesting data about this type of nanoparticles, hybrid nanoparticles, but using cells. And here we can see that in worms, we observed a decrease in their survival rate from 10 micrograms per ml. And if I recall, I think the concentration was pretty similar from the cells. Okay, so we can see that the results found in worms, they are quite similar to what happens in cells. So this is important as well. We also analyzed the size of the progeny. We call it brood size, is a reproductive assessment. And we observed that there was only a decrease from 50 and 100 micrograms per ml. So from lower concentrations, these nanoparticles, they are safe. It would be interesting to analyze the same assays using these nanoparticles, but produced not by biogenic growth. So we could analyze the effect of the green tea and the polyphenols present in green tea. We also analyzed the localization of a very important transcription factor, a very important antioxidant transcription factor. It's important that this DAF16 migrates to the nucleus so the organism can defend itself against something, some hazard. So we could see that the treatment with 10 and 50 micrograms per milliliter increases the nuclear migration of this factor, which suggests that the worm is suffering something and it's trying to defend itself against. But this happened only at the higher concentration, okay? We also look at apoptosis. It's something else that we can see using green fluorescent protein, using these transgenic animals. So we expose them and then we analyze the number of apoptotic corpses. And we did not find any alteration. So there is no apoptosis in this treatment. We are doing other experiments. I'm not going to share now because of the time, but we are very excited about this collaboration. We are also analyzing some silver nanoparticles, only silver nanoparticles produced by the same biogenic growth, and we can analyze the difference between these nanoparticles and the hybrid nanoparticles. We also have a great interest in nanopesticides. We all know about the great advantages of using nanopesticides reducing the losses of the pesticides that are encapsulated, more efficient application, etc., but we need to analyze the environmental footprint, the environmental impacts of these nanopesticides. So it's very important to study that, to know what's going to happen in the environment. So first, we started this collaboration with Professor Leonardo Frassetto, and he gave us some nanoparticles that were made with PCL, polyepsilon caprolactone. We knew that PCL was it caused some toxicity to the worms. So he gave us these empty nanoparticles, and we also analyzed those loaded with atrazine. And we noticed that both nanoparticles had the same toxicity pattern, as you can see here. So, well, something is happening. Why only the empty nanoparticles are causing this? We look at reproduction, and we saw that the empty nanoparticles even caused higher toxicity than those loaded with atrazine, okay? And we did this exposure using it's very important to highlight, we used a nematode growth medium, which is based with agar, okay? We also analyzed only the pesticides at the same concentrations that we tested the empty nanoparticles, and we did not find any toxicity caused by the pesticides, the free pesticides. So actually, the toxicity that we were observing here was because of the PCL. We were exposing the worms for 48 hours here, okay? We also analyzed the size of the worms, so their development. And we noticed that the exposed worms, they had smaller sizes. You can see here both empty PCL nanoparticles and also those loaded with atrazine, same pattern. So a big effect on development. This was quite bad. And we also analyzed it, we functionalized these nanoparticles, and we added rhodamine, if I recall, and we could see a different pattern from the other picture that I was showing you. You can see that everything, all the nanocapsule is in the gut of the worm. So we do not see the absorption and the distribution of the content. So maybe there is some interaction of these nanoparticles with the tissue from the intestine. So maybe this is causing the toxicity that we observed. We were very upset because we observed this with a PCL. We also observed this we used another 2 different solutions, nanoformulations, another one with chitosan and TPP. And also we observed toxicity. So we were like, wow, very upset. But then Leonardo's group sent us another set of nanoformulations, but this time these nanocapsules, the polymer used for these nanocapsules was zein, which is a natural polymer from corn. They loaded these nanoparticles with neem oil, which is an interesting bioinsecticide, and we analyzed the safety of these nanoparticles. As you can see here, only the empty nanoparticles are called NPs here, okay, only the empty nanoparticles in purple. You can see that there was no effect on survival, no effect in body length, no effect in reproduction, no effect in the movement of the pharynx, because the worm is always pumping the pharynx, and it's important to see if the worm is ingesting the nanoparticles. No effects of the empty nanoparticles. So this means that zein is not toxic. And then we were very happy about the results. We were very excited about zein. And okay, we observed no toxic effects of neem oil when encapsulated with this material. And this study was part of a thesis from Monica Pascoli, and this study, her whole thesis was awarded, and it's very. I was very happy to be into this work here. Here you can see the expression of glutathione transferase, which is a very important detoxification enzyme. And here we saw that only neem oil azadirachtin was caused a decrease in the fluorescence of glutathione transferase, which would be bad for metabolization of xenobiotics in the worm. But when we gave neem oil into the zein nanocapsules, we did not observe this alteration. So here it indicates that there was a protection of the worm when exposed to these nanoparticles. So again, very excited about these results. I'm going to tell you, of course, some of the challenge because this is important, okay? The worm's physiology, of course, the worm is an invertebrate. It does not have a liver. It does not have lungs. It does not have a brain. But for example, the worm has the metabolizing enzymes distributed in the body. So it does not have a liver, but it has many cytochrome P450 enzymes, okay? The worm does not have a brain, but has many neurons, and many of those neurons are present in our physiology as well. So there are many similarities, but of course, there are challenges here. The worms, they do not have a bloodstream, so we cannot see very well the distribution in the blood. We see distribution across the tissues, okay? So something else is the exposure protocol. I mentioned to you that we were using an agar-based medium, but now we are standardizing a method which we expose the worms in the soil. So we make like a soil solution, we expose the worms, and then we transfer the soil to the NGM plates. And then the worms, they crawl from the soil to the agar, and we can analyze the physiological parameters that I showed you before. So it's very interesting to analyze this, considering that, especially for nanopesticides, considering the exposure, and it would be interesting to analyze in a real environment, okay? Something else, the absorption distribution of the nanoparticles is another challenge. Usually we have to functionalize the nanoparticles, to analyze that, but I would like to see the tissue distribution of the nanoparticles. Are they going to the neurons? Are they going, staying in the gut? Are they going to the reproductive system? It would be so interesting to analyze that, particularly for those inorganic nanoparticles. Where is the iron going? Where is the silver going? This would be very interesting to see, but this is still a challenge. And also the polymers, they can, and tensioactives, they can be particularly toxic to worms, but this is something very interesting to analyze, because we need to know how these polymers and tensioactives used for the nanoparticles, for the nanocapsules, etc., how they are affecting the environment, right? So it's important to know, and the worm is part of the environment, especially the soil. So I hope I convinced you that the worm is an important animal to do this analysis. And we are expecting collaborations. I would like to show you where Universidade Federal do Pampa is a new, very young university. It has 12, 13 years only. It's in the southern part of Brazil. I'm here in Uruguaiana, border with Argentina and Uruguay. I don't know if there's anyone from these countries here. So I understand the Spanish, but by Spanish, I don't speak very well. Here is my contact. Okay, here is the view of the university. We have many rice crops here. This is the group. I would like to thank the groups and all the collaborators that send us the nanomaterials, and thank you all the funding agencies, and thank you for the attention.
Okay, thank you very much, Diana. A question?
Okay, so we have a question here. Bruna Freire said, congratulations for the presentation, Diana. And the question is if C. elegans could be used as a model for the evaluation, for the use of nanoparticles for the treatment of diseases, neurodegenerative diseases, I mean.
Yes. You know, we have many models, transgenic models for Parkinson's, Huntington's, Alzheimer's. So we can observe phenotypical changes, and we can treat them with different types of nanomaterials, with different types of drugs, you know. So yes, we have many models for that. So I think that was her question, right, about the models and the possibility to treat them, right? I don't know if I answered everything.
Thank you very much.
Mm-hmm.
Are there other questions? I think
no more questions. Diana, congratulations, excellent.
Thank you for the collaboration.
To see you here, and yeah, we need to go further with this. We have new nanoparticles and new models that we can explore, and I hope to finish this work and then we can move on, because now with Joanna, Isabella, we have new kinds of nanoparticles to be explored. It's amazing. It's very nice, beautiful work with all those images, and congratulations.
Yeah. No, it's great. So I'm open to collaborations. That's why I was jumping from study to study. So I would like to show you what we can do with this great model.
Excellent.
I thank you. I thank you for this opportunity.
Okay, no more question. Bien, muchas gracias, Diana, por tu presentación. Y continuando con nuestro programa, a continuación vamos a ver 3 presentaciones a cargo de la doctora Marcela Milasoto de la UFABC, el doctor Andrés Quirós de la Universidad de la Frontera y el doctor Edgar Uquiche, quienes nos van a presentar una breve reseña de los 3 programas de doctorado que han patrocinado y han hecho también posible la realización de este evento. Y finalmente, los invitamos, ¿no es cierto?, a seguir con nosotros, ya que finalmente la doctora Medea Seabra va a dar una información muy importante, así que los invitamos a permanecer acá. Entonces, para continuar, vamos a presentar a la doctora Marcela Milasoto, quien nos presentará el Graduate Program in Biotechnoscience de la UFABC.
Hello, everyone. Can everybody hear me?
Yes.
Yes. Okay, so first of all, I would like to congratulate the organizing committee for this excellent event. This is my first time in an event in this field, and I'm having an amazing time. So congratulate for that. And I'd also like to thank for the opportunity to present the graduate program in biotechnoscience at UFABC. To start my presentation, I'd like to present the Federal University of ABC, which is a relatively new university in São Paulo State in Brazil. We started our academic and research activities in 2006, so we just formed a team in the last September. And UFABC was created in a new organizational perspective based on an innovative interdisciplinary plan. And to stimulate that, we have no departments, but 3 centers in an attempt to encourage the integration of members from different backgrounds. For example, the Center of Natural and Human Science, which I belong to, consists of almost 300 professors from different backgrounds, as biologists, chemists, physicists, among others. And this environment are quite rich for addressing research problems. And in this context, our graduate program was created by joining academic excellence in the field of natural and human science, and also interdisciplinary scientific collaborations. And to foster that, our labs were designed for interdisciplinary research, since they are shared for 2 or more researchers from different fields. And we also have an amazing multi-user facility of equipments, and also an innovation and technology agency, which is very active in protecting new technologies and also transferring these technologies to our industry partners. In the research environment, our program acts based on 3 core values. The first one is biotechnoscience, because we believe that bio and nanobiotechnological tools are the best solution to improve life quality. Also innovation, so our research is focused on developing new bio and nanobiotechnological tools, proposing solutions for agribusiness and animal and human health. And also sustainability, that we know that is a very important topic to be discussed nowadays. And we work for the development of research with focus on maintaining available natural resources. And within these values, our students are stimulated in 3 main perspectives. The first is excellence, by allowing students to be effective and seriously engaged partners in highly creative projects to tackling some of the most complex problems in biotechnoscience. We also stimulate curiosity by understanding the multifaceted aspects of biotechnology in its critical context for interpretation, including but not limited molecular and cellular aspects, but also social observations. And innovation, by developing experimental approaches and new tools to address biotechnological problems, ranging from the atomic and ultrastructural levels to model organisms. We develop research with focus on 2 main fields. The first one is agriculture. In this field, we have projects related to plant and animal biotechnology, biofuels and sustainability, and also healthcare, with projects in the field of human and animal healthcare, diagnosis, toxicology, and biopharmaceuticals. And our solutions include nanobiotechnology-based strategies, recombinant DNAs and proteins, and also social aspects in projects involving innovation management in biotechnology. In this case, we have projects in RDI management, economy sustainability, and also innovative strategies. Strategically, our program operates in 6 fronts. Interdisciplinary research through collaborative projects, and also offering a rich environment for cross-disciplinary research and courses. Also opportunities by offering outstanding research and mentors, high-quality research labs, industry partnerships, scholarships, project funding, and financial support for events. We also promote events like workshops and seminars. And recently, we are now disclosing our news through our social media, and that includes publications, patents, events, and opportunities. And all these strategies are continuously monitored in order to offer to our researchers and students an excellence environment. And our last strategy, and perhaps the one that most interests everyone here today, is our internationalization projects. We currently have collaborative projects with 11 countries, like Canada, US, UK, France, Germany, Czech Republic, Italy, Portugal, Spain, and our neighbors Chile and Argentina. And these projects include co-tutel and joint PhD. In this case, we have joint supervision by professors in 2 institutions, one here in Brazil and another abroad. And the candidate graduates from both universities. We also offer seminars and labs, which are remotely accessible for research community. And YPBC offers language courses like Spanish, French, English, and Portuguese for foreigners as well. Our program is also part of the CAP Sprint project, that is an institutional internalization project, which includes funds for work missions, project maintenance, scholarships abroad for students here in Brazil, like sandwich doctorate, and also for professors, like senior and junior visiting professors, and also scholarships in Brazil for visiting professors working abroad, and young talents and postdoctoral researchers. To join us, I invite all of you to check our website. So if you are interested in our master or doctorate courses, our next selection process will be in January 21, with admission in May 21. We also have continuous positions available for postdocs, And if you are a researcher, I invite you to take a glance in our events programming and also our opportunities. I want to finish this presentation by sharing some pictures of our students, professors, labs, facilities, and invite all of you to come to one of the top public research universities in Brazil. Here are our contacts, so our website, our Facebook and Instagram. And if you have any question, we have our institutional email, that is ppgbtc, and also my personal email, that is marcela.milasotto. So thank you all for the attention.
Thank you, Marcela, for this nice presentation of our graduate program at Federal University of ABC. And Gonzalo?
Sí, any question? ¿Alguien tiene alguna consulta? No question. Any question can be made by email also.
As we can see at our institution, we have a very international and interdisciplinary courses. So we are very open for new students, exchange and international internship. So if you are interested, please contact us.
Yes, our website and Instagram and Facebook and also the email will be in the abstract book. So I invite you all to take a look at our website. We are very open for collaborations and for exchange experience and students and professors. So feel free to contact us.
Okay, thank you, Marcela. Ok, entonces, continuando con las presentaciones, vamos a dejar con ustedes al doctor Andrés Quirós, que nos va a presentar el programa de doctorado en Ciencias de Recursos Naturales de la Universidad de la Frontera. Doctor Quirós, muchas gracias por estar acá con nosotros y puede comenzar a compartir su presentación. ¿Estás sin audio, Andrés?
El audio. Gracias. Gracias, Gonzalo, por la invitación. Agradezco mucho que nos haya dado la oportunidad para mostrar nuestro programa. No pocas veces se hace, pero sí, eso lo agradezco muchísimo. La presentación la diapositiva está en inglés, pero voy a tratar de hablar en inglés y en español. Bueno, este programa nace hace casi 20 años atrás, ¿ya? Es un posgrado de provincia, y un poco para contextualizar, los posgrados de provincia siempre han estado un poco dejados de lado a nivel nacional, educacional, digamos, en Chile. Por lo tanto, hacer posgrado y hacer investigación en provincia ha sido muy complicado. Y ese es uno de los valores que tiene este programa, que ya lleva 20 años. El próximo 24 de abril cumplimos 20 años. Y se ha logrado posicionar de una buena forma y de una excelente forma en Chile. El objetivo que se creó, que se pensó al principio, hace 20 años atrás, cuando se creó el programa, era crear un programa multidisciplinario que se enfocara básicamente en el apoyo a todo lo que son procesos productivos regionales y nacionales, y enfocándose básicamente en las ciencias del suelo, pero posteriormente comienza a extenderse a una serie de campos que hoy en día ya abarcan prácticamente casi todos los niveles de las ciencias básicas, ¿ya? Biología, microbiología, físico-química del suelo, ambiente, nutrición y fisiología de plantas, química ambiental, biotecnología, química ecológica, bioproceso, todo ello para tener una agricultura sustentable, biotecnología en la producción agroalimentaria, manejo de residuos, bioenergía y energía. O sea, es un programa que está enfocado a todos los problemas, digamos que, a tratar de solucionar todos los problemas que como sociedad que la sociedad nos exige, ¿no? Esa es nuestra misión, básicamente. Bueno, como un esquema ahora para presentar cómo nosotros como programa, que estamos insertos en la Universidad de la Frontera, que es una universidad de provincia, como decía anteriormente, es una universidad estatal, tenemos un esquema un poco complejo en el sentido administrativo, en el sentido de tener varias secciones, donde tenemos un cuerpo académico, el comité académico, que somos 6 personas, hay 4 personas, hay 4 académicos, más el directorio y un subdirector, pero lo relevante de este programa es que hay una sección que apoya con fondos del programa, y que son fondos destinados para la habilitación del inglés que deben tener nuestros alumnos. Y ello está estrechamente relacionado, obviamente, con lo que nosotros pretendemos con un programa, que es la internacionalización y todo lo que son las pasantías internacionales, que las vamos a ver en detalle más adelante. Bueno, este doctorado tiene una componente, digamos, tecnológica bastante importante, y por ello está apoyado por un núcleo que es el BioREN, de la Universidad de la Frontera, que es nuestro soporte tecnológico, y que tiene varias unidades, digamos, que contienen todo lo que es el equipamiento mayor de la universidad, como citometría, proteómica, metabolómica, microscopía. También hay una colección nacional de cultivos reconocida internacional en el mundo, físico-química y análisis de partículas, genómica, etc. Ellos nos aportan todo lo que es la parte de la instrumentación mayor. Una cosa importante decir de este doctorado, este doctorado está sometido a todo lo que es un proceso de acreditación nacional. Y siempre cuando me invitan a hablar del doctorado saco esta diapositiva, ya que competimos con las grandes universidades chilenas, que son la Universidad de Chile, la Pontificia Universidad Católica, y la Universidad de Santiago de Chile, Universidad de Concepción, la Universidad Federico Santa María. Esas son las principales universidades en Chile, las que tienen mayor productividad. Y ahí estamos nosotros, una universidad de provincia, con nuestro doctorado, que tiene una acreditación de 8 años. Eso es un logro bastante importante, ya que estamos posicionados dentro de todas las grandes universidades, y si miramos la gráfica o la tabla, vemos con detención de que estamos también compitiendo y reconocidos en el rol en la sección de que son las ciencias básicas, como física, química, biología, etc. Es un doctorado que tiene un alto reconocimiento a nivel nacional en este momento. Por eso siempre saco la luz de esta diapositiva, y nos sentimos muy orgullosos de lo que se ha logrado a este respecto. Otro aspecto interesante es que este doctorado surge con 2 o 3 áreas de investigación, y con el tiempo, después de 20 años, ya tenemos 8 áreas de investigación, que es la que ustedes observan en pantalla. Esta figura la elaboré hace un par de días atrás, y muestra lo que realmente somos, es decir, que todas estas áreas están de alguna forma interconectadas, y todas van en el bien, digamos, de la producción, de incentivar y de la innovación, y de incentivar también el descubrimiento de nuevos procesos, de nuevos productos que se apliquen a lo que son los procesos de producción de materias primas o de alimentación. Estamos también con una nueva área de investigación, que es el cuidado de los recursos hídricos. Como decía anteriormente, una de las cosas que también nos llena de orgullo es todas las relaciones internacionales que tiene este doctorado, que se reflejan en esta diapositiva, y son todas las relaciones que tenemos con diversas universidades del mundo, donde nuestros alumnos van a realizar pasantías. Además de ello, están las colaboraciones directas con cotutelas y con, programas con doble titulación, que son las que muestro a continuación, que son con la Universidad de Leuven en Bélgica, con la Universidad Católica de Sacro Sucre en Italia. Son todos convenios que tenemos con doble titulación o cotutela. La Universidad de Granada, la Universidad Federal de Amazonas en Brasil, la Universidad Pierre-Marie Curie, Francia, y la Universidad degli Studi di Napoli de Federico II. ¿Se me queda algo? Y una universidad, la Universidad de Minho en Portugal. Nosotros estamos incentivando este tipo de colaboraciones, tenemos convenios establecidos, estos convenios están vigentes, los alumnos nuestros van a esas universidades, se involucran en el currículum de esas universidades, y los alumnos de esas universidades pretendemos que comiencen a venir a nuestra universidad para que obtengan la doble graduación. Otro aspecto interesante a destacar de nuestro doctorado es el número creciente de alumnos que estamos teniendo en el transcurso, digamos, de vida de este doctorado que nace en el 2001. Y a la fecha tenemos 112 graduados para la Universidad de Provincia, y para cualquier doctorado nacional este es un número bastante importante. Y este hecho sí es bastante relevante para la Universidad de Provincia, que todos nuestros estudiantes de doctorado han aportado durante estos últimos años con 350 publicaciones de primer nivel, y el staff académico aproximadamente con 1.550 publicaciones. O sea, cuando nace este doctorado, lo que provoca en la universidad es un impacto realmente significativo en lo que es la producción científica. Bueno, era una presentación que me agradezco a Gonzalo, ¿no es cierto?, por haberme invitado, por preparar, digamos, en los últimos días, así que muchas gracias, Gonzalo, por la invitación, y eso sería. Gracias.
Muchas gracias, Andrés. ¿Tenemos alguna consulta?
Una pregunta se puede hacer nuevamente por los medios descritos.
Si no hay consultas, recuerden que pueden escribir. Ambos doctorados han presentado ya, hay páginas web, hay emails, si tienen alguna duda respecto a los programas que se han presentado. ¿No hay consultas? Parece que no. Bueno, muchas gracias, Andrés, por tu tiempo.
Gracias por la presentación, profe.
Bien, continuamos con la siguiente presentación, que estará a cargo del doctor Edgar Uquiche, director del programa de doctorado en Ciencias de la Ingeniería, mención Bioprocesos. Gracias, Edgar, por compartir con nosotros acá en este workshop.
No, más bien gracias a ustedes por la oportunidad, ¿no? Hay siempre pocas instancias, pero yo se los agradezco en nombre del programa. Bien, nuestro programa es en Ciencias de la Ingeniería, mención Bioprocesos. Es un programa nuevo, el programa, perdón, no sé. Ok, el programa se creó en el 2015, nace en el seno del Departamento de Ingeniería Química adscrito a la Facultad de Ingeniería y Ciencias. Es un programa que nace para fortalecer las líneas de investigación que ya existían en el cuerpo académico del departamento. Si bien el programa es nuevo, el Departamento de Ingeniería Química está cerca de cumplir los 30 años. Como departamento asistimos a varias carreras de la ingeniería, como ingeniería medioambiental, ingeniería de biotecnología, ingeniería química, y también asistimos a un magíster en Ciencias de la Ingeniería, mención Biotecnología. Esto crea un ambiente multidisciplinario. En los laboratorios coexisten estudiantes de pregrado y posgrado, lo cual es muy provechoso para su formación. El objetivo principal de nuestro programa es formar investigadores que sean capaces de proponer investigación relevante, original, independiente y con resguardo ético. Y dos líneas que sustentan este programa es la ingeniería y bioprocesos en alimentos y la ingeniería y bioprocesos ambiental. Estas dos líneas se subdividen en las siguientes sublíneas, que es nanobiotecnología y biotecnología ambiental, donde participan Gonzalo Tortela, la doctora Cristina Díez y la doctora Olga Rubilar. Bioenergía, y en la sublínea de ingeniería y bioproceso de alimentos están las sublíneas fermentación y modelamiento de bioprocesos, bioseparaciones y encapsulación y procesamiento de alimentos. Nuestros alumnos tesistas, todos participan en estas sublíneas, y estas líneas de acá son sustentadas por profesores con capacidad productiva en publicaciones y en proyectos. Uno de los requisitos principales para postular este programa es poseer un grado de licenciado o de magíster en ciencias, en áreas asociadas al programa, como son ingeniería en alimentos, ingeniería ambiental, ingeniería química, ingeniería bioquímica, ingeniería de bioproceso y biotecnología, y otras similares en el área de la ingeniería. Nuestro programa tiene una duración de 4 años, divididos en 8 semestres. El primer año es un año de asignaturas, donde 6 asignaturas son de formación obligatoria, ligadas a la ciencia de la ingeniería y procesos, y 2 asignaturas electivas. Tenemos una batería de 12 asignaturas electivas, las cuales están asociadas a las líneas y sublíneas de investigación. Posteriormente, el tercer semestre es un semestre en que el estudiante elabora su proyecto de tesis y lo defiende en un examen de calificación. Aprobado este tiene 2 años y medio para realizar la tesis de doctorado, y entre los requisitos está tener una publicación y una publicación enviada, ¿no?, en una revista de alto impacto. Los avances de tesis que se muestran acá corresponden a un monitoreo para ver el avance del estudiante conforme a su plan, a su carta GAN propuesta en su proyecto. Los estudiantes, el financiamiento para este doctorado principalmente proviene de becas externas otorgadas por la Agencia Nacional de Investigación y Desarrollo. El 80% de nuestros estudiantes poseen esta beca. Una es la beca de doctorado nacional y la otra es la tesis de doctorado en el sector productivo. En el caso de no adjudicar, nuestra universidad otorga becas por parte de la Vicerrectoría de Investigación y Posgrado, becas de arancel y becas de manutención, las cuales se renuevan cada año conforme al rendimiento académico del estudiante. Nuestro claustro académico está conformado, nuestro cuerpo académico está conformado por 16, los cuales provienen de importantes universidades del país, también de Brasil y también de Europa. Los estudiantes de nuestro programa pueden también participar en universidades o centros de investigación internacional a través de convenios que tiene nuestra universidad, ¿ya? En importantes universidades de Brasil, como Campinas, Pernambuco, Universidad de Sao Paulo, Universidad de Santa Catarina, universidades de Europa y de América Central. Esto es importante, ya dado que uno de los propósitos y objetivos de nuestro programa es la internacionalización. La infraestructura que asiste a nuestro programa proviene principalmente del Departamento de Ingeniería Química a través de sus laboratorios, del Núcleo Científico y Tecnológico BioREN, el cual tiene varios centros, pero 3 centros de ellos están asociados a nuestro programa, como el Centro de Biotecnología, Alimentos y Bioseparaciones, en el cual participo, en el Centro de Manejo de Residuos y Bioenergía, y en el Centro de Excelencia de Investigación Aplicada en Biotecnología al Medio Ambiente. También del Instituto de Agroindustria, y junto con nuestro programa, 2 programas más, podemos hacer uso de un edificio de doctorado, el cual cuenta con salas de clase, auditorio, donde se realizan avances y exámenes, sala de reuniones y oficina para profesores visitantes. Aquí listo los laboratorios con que cuenta el Departamento de Ingeniería Química para ambas líneas, en bioprocesos en alimentos y bioprocesos en ambiente. Todos estos laboratorios están a cargo de profesores del staff del claustro, los cuales, en el cual también desarrollan su tesis, no solamente estudiantes de doctorado, sino de magíster y de las carreras que mencioné anteriormente. lo cual crea una interacción interesante, ¿no?, y provechosa entre los estudiantes. El núcleo científico y tecnológico BioREN cuenta con laboratorios con equipamiento mayor que sirve para apoyar la investigación de los académicos de forma transversal en la universidad, y tiene unidades importantes como de microscopía, confocal, electrónica, fluorescencia. Tiene una unidad de análisis de partículas y cromatografía, y cuenta con una unidad de genómica, proteómica y metabólica. El BioREN cuenta con investigadores asociados y con un cuerpo técnico, el cual asiste, ¿no?, en los análisis. El Instituto de la Industria, también los académicos del Departamento de Ingeniería Química participamos en este instituto. El año pasado se inauguró una planta piloto, la cual tiene toda una línea de procesamiento de jugos, de empaques y de secado, ¿ya? Y esto proviene de un proyecto Z, proyecto de tecnología de alimentos, en el cual profesores del staff académico participamos. Las actividades del programa, también en conjunto con otros 2 programas más, se realizan en este edificio, el cual cuenta, como les dije, como auditorio, donde se realizan avances, exámenes, salas de reuniones y 2 salas de clase con equipamiento multimedia para esos propósitos. Una cosa interesante es que la universidad cuenta con un centro de transferencia tecnológica. En los últimos meses hemos estado en contacto con ellos. Ellos prestan servicio en todo lo que es transferencia tecnológica, vigilancia tecnológica, monitoreo de proyectos I+D, patentamiento, y ellos han apoyado y hacen seguimiento a las tesis que estamos generando en nuestro programa. Este año, nuestra universidad adjudicó, bueno, en el país, FONDEF, VIEW, son proyectos de vinculación con la industria. En este año se otorgaron 20 proyectos, de los cuales nuestra universidad adjudicó 6, la mayor en el ámbito nacional. 2 de esos proyectos son de nuestras 2 primeras egresadas. Carla Duarte, con un proyecto de bioprecipitación de minerales de residuos de la industria minera, y Fernanda Pinto Ibieta, con su proyecto de obtención de ácido olívico a partir de residuos de melaza. Ellas son nuestras primeras graduadas en nuestro programa. Carla lo hizo a inicios de año y Fernanda lo hizo ahora en octubre. Y con gran satisfacción, ¿no?, estamos muy orgullosos de ellas, de lo que han logrado. Finalmente, nuestra universidad, Temuco, se encuentra en una ciudad moderna, con servicios, con lugares de comercio, y también rodeada de un entorno natural precioso, que es muy atractivo, ¿ya?, rodeada de lagos, ríos y ciudades bastante turísticas. Nuestro programa hace su convocatoria todos los años, y la convocatoria finaliza a fines de octubre. La dirección se muestra acá. Es un programa que está acreditado por la CNA, tiene 3 años de acreditación. Es el año máximo que se le puede otorgar a un programa que no tiene graduados. Ahora, con nuestras 2 primeras graduadas, podemos postular a más años de acreditación. Más información, bueno, ahí está el correo del programa y también en la página web. Solamente reiterarles las gracias, ¿no es cierto?, por esta oportunidad y esta instancia. Muy amables.
Ok, muchas gracias, Edgar, por la presentación. ¿Tenemos alguna consulta?
Bueno, de todas formas, ahí llega el correo electrónico.
Sí, para cualquier consulta, sí. Muchas gracias, Edgar, nuevamente.
Gracias a todos.
Ahora quiero dejar con ustedes a la doctora María Cristina Díez, directora del CIBAMA, quien se dirigirá a ustedes para dar unas palabras de agradecimiento en este workshop. Doctora Cristina Díez.
Gracias, Gonzalo. Bueno, first of all, thank you very much for the participation of our invited speaker, a great number of researchers in general, and for the large audience in our first Latin American Congress on Nanobiotechnology. We are happy for the excellent organization with the participation of the Universidad Federal do ABC and our Cibama UFRO Center in this event. Special thanks to Gonzalo, Olga, Deya, and as well Paola, Carla, and the other students, and all of that participate in this, in the organization of this event in general. Thank you very much, and special for Nelson, our guru in this business of nanobiotechnology. And thank you for all of us for your participation. Obrigado, and muchas gracias. Congratulations.
Thank you very much, Cristina, for your work.
Gracias, Cristina. Gracias, Cristina.
Ok, entonces, para finalizar nuestro evento, vamos a dejar a la doctora Amedea Seabra, quien dará un mensaje de clausura y un mensaje para lo cual yo voy a compartir una lámina acá con ustedes. Mientras...
Yeah. Okay, so first of all, I'd like to thank you for all the presentations, the poster, oral presentations from the researchers, from the professors, from the students. Very nice. And this workshop was supposed to be in Chile, at Pucón, a nice city. But under this circumstance, under this scenario, unfortunately, we are not allowed to travel. But anyway, I think there was a very important and nice experience that works. We are able to put all together researchers from Chile, Argentina, Mexico, Portugal, Spain, so very international. And the idea here is to continue. So we are thinking about not to be an isolated workshop, but as we work together, so all the invitations here, the presentations, somehow, in some extent, we have been working together. So the idea is to increase our collaboration and to create kind of an networking. So Latin America network on nanobiotechnology, or international, Latin America or international maybe. So the idea is to continue this kind of events, this kind of workshops, seminars between us, student internships, and also search for grants, proposal calls, project togethers for financial supports. As Marcela explained, here in UFABC, we do have CapSprint. This is an internalization program, so we are allowed to send PhD students from UFABC abroad. As well, we can go ourselves, professors. We can receive professors from abroad, from other institutions. So the idea is to we can, I think as we have been working together, we can do more. And we should look for new applications and call. So our idea here is to formalize this kind of network. Maybe we can involve the graduate programs from UFRO, from UFABC. We can think some kind of official, to have an official network. So we can thinking about this. This is kind of a task for us to do, to thinking about this. So the idea is to continue this collaboration between us. So, and we have so many students from UFABC, from UFRO, from Mexico, and it was very nice. And I would like to thank the organizer as well, especially Gonçalo, Professor Gonçalo Tortella, Olga Rubilar, Maria Cristina, all the team. Together we have a project like FAPESP CONICIT with, I do have a project with Olga Rubilar. So the idea here is to continue, and I hope that every 2 years, I think, we can have this kind of workshop. So let's thinking about the second workshop, and maybe we can switch the places, Chile, Argentina, Brazil. Even in Brazil, we have researchers from Sorocaba, from Londrina, and Unicamp, UFABC. So that's the idea. And I hope to put people together to connect people. The idea here is to connect people. So I hope that you enjoy this conference, and I hope that we can continue working together. Gonçalo? No, I cannot.
Silenciado.
Very nice initiative, Dea.
Sí, Cristina. So the idea is to continue working together. I think we are a great team. I'm very happy to work with all you guys, and I think we can be stronger together. I have been learning a lot working with you, so with all your team, and so that's the idea.
Okay, thank you very much to all for the opportunity. Well,
we don't have any food here, so we were supposed to have some drinks, some food, but unfortunately, this is a very cheap workshop. So now you go for your lunch by your own, and that's it.
So, Andres?
I am a little confused because there is a proposition from Amedea, sorry, to create a Latin American network. So this is your proposal, but what is the next step? I mean, is now to all the audience to validate your proposal, your proposition, or start to work in the creation of this this Latin. I am agree. I'm happy of that. So I'm very happy, and our program would be happy to participate in your idea. So I am completely agree. But I'm not sure about what is the next step. You know, I know if you don't understand me. I mean,
yeah,
what is the next step?
I know your question. That's my question too. Yeah, for instance, here at my university, I can include. I included UFRO in this internalization program that Marcela presented here at my institution.
Okay.
So I can extend this to other universities in Mexico, in Argentina. With this, we can exchange students. It's something official that we can exchange visiting students, and we do have grant for this.
Yeah. So I think because I know how is the rules of our university for doing of this kind of thing. And then we have first we have to elaborate some kind of agreement between PhD programs or between universities. Because if we don't have this kind of agreement between a university of a specific PhD program, it's a little bit difficult to establish this kind of internship, interchange, student internship.
Yeah.
So this is, I think, is the first step. Is to
make it
to establish, the proper or the formal agreement between universities, maybe, or specifically between the PhD program. So, and then we can talk about the rest of the thing related to this kind of Latin American network. I think this is the first step. You know, is
we need to have something official in between our institution and. On my side, and I think in RIFRO is the same. We can do this. We have an office, international office, that can deal with this. So this is not we have a paperwork to do, but it's okay to have something official, right? And then, of course, we can apply for grants, scholarships, and
because if you don't do that, it's like it's the same that we used to do. I mean, I sent one of my students to this university, and there is no any proper program, and nobody knows about that.
Yeah, exactly. Yeah, we have been working with a student exchange, but we need to make it official, because this is very important for our institution. In Brazil, it's very important to have this official, to officialize that we have this collaboration, we are exchanging students. It's very important. So we need to work on this for sure.
That's right.
Yeah. Paperwork.
Sí, Cristina?
I propose that that this commission that organized this first event can prepare some print or some borrador, and we analyze and we approve. I think it's because we have a lot of similar agreement in general with other network and with our doctoral programs in general. I propose that this commission prepare something for us to analyze.
Mm-hmm. That's good. That's good. Very good.
Ok. Bueno, entonces vamos a seguir trabajando para que esto se formalice. No sé, ¿cómo? La foto, sí. Gerson, Alay, no sé si están presentes.
Alay, Gerson, quem tiver. Marcela, pode entrar.
Ahí está, Alay.
Ok. Gerson creo que falta, ¿no? Bueno, lo esperamos. Foto, 1, 2, 3.
Nossa Senhora.
Saudades.
Qué legal.
Ok, muchas gracias. Bueno, vamos a seguir trabajando para que esta red se pueda ser una realidad, ¿no es cierto? Bueno, ya la red existe, pero como decía Andrés, hay que formalizar algunas cosas. Eso no es, a veces no es muy rápido, pero podemos ir trabajando, ¿no es cierto?, desde ya en ir organizando.
It's fast. Now the university have a lot of experience, so we can do that in a short time.
Yeah, I think so.
If we are everybody is agreed, so it's very fast. It's no problem.
Okay. ¿Quién se va primero?
Sí, ok, bueno, muchas gracias a todos. Thank you very much to all.
Chao.
Le vaya muy bien.
Bye.
Chao.
Chao.